Bonding is favorable because it forms compounds that is more stable than individual atoms from which it is made. And chemical reactivity is based on, like you can explain the chemical reactivity using the electronic configuration of the atoms.
කන්න ඔව් පොඩ්ඩ මට මං කාගෙන යනවා මට පොඩ්ඩ නෑ මට පොඩ්ඩ හරියන්නේ නෑ උඹ වංශ පොඩ්ඩ කාන්න මට දෙන්න ඇයි
Please keep muted because you will be disturbing the others. So please see whether you're muted. If you have a question, of course, you can unmute and ask. Otherwise, please stay muted. Can you see the slide?
Yes, madam.
You can, right. Chemical reactivity, yes. So, yes, so you learned about electron configurations yesterday, and actually atoms try to combine with that is they react or form bonds with other compounds in order to achieve a more stable electron configuration. More stable electron configuration.
Recording in progress.
Achieve a more stable electron configuration. Actually, the most stable electron configuration is the electron configuration in which the outermost shell, the S and P orbitals of the outermost electron shell, if it is full, if the S and P orbitals of the outermost electron shell, if it is full, then the element, the atom is very stable. So that is what the atoms try to achieve in forming bonds. So let's take sodium. It has an atomic number of 11. Electron configuration is given here. 1s2, 2s2, 2p6, and 3s1. Right? So when this atom or any atom tries to form bonds to become stable, actually it is the electrons in the outermost shell that is involved. Right? In this case, we know that the outermost shell 3s1, 3s has one electron. So this is either given or yes, this is actually given, because otherwise to fill the 8 electrons, this atom has to obtain 7 electrons, 7 more electrons. If it has to have a if this atom wants to have a full outermost shell, that will be 3s1 and 3p6. So to achieve that electron configuration, sodium atoms should have sodium atoms should obtain 7 more electrons. So that is actually very difficult. So what the sodium atom does is that it loses an electron. It gives an electron away, right? And then it forms sodium plus because it has lost an electron. It forms sodium plus ions, and like the example that I showed you previously, sodium chloride, it forms an ionic bond with chloride. Of course, not only with chloride, it can actually form bonds with fluoride, bromide. So you learned the electron configurations, the periodic table, and we know in the 7th group, there are many elements such as fluorine, chlorine, bromine, iodine. All the atoms can actually receive 1 electron. Then they will have 8 electrons on the outermost shell. So actually, now if for example take chlorine, it obtains this electron, so it will have 8 electrons on the outermost shell. Likewise, sodium will have 8 electrons in the outermost shell, because when it loses this electron, 3s1, right? It loses this electron 3s1. Then what is the outermost shell? What is the outermost shell? When 3s1 is gone, what is the outermost shell of sodium?
2p.
Yes, the second electron shell, the second shell, electron shell, the second level, 2s2 and 2p6. That is the outermost shell, right? 2s2 and 2p6. That is the second electron shell becomes the outermost electron shell. So in this case, when 3s1 is gone, there are 2 electrons in the s orbital and 6 electrons in the p orbital. Altogether, there are 8 electrons in the second electron shell. In the second shell, 8 electrons. I told you when the electron shell is full, the atom is happy, it is stable. So when 3s1 is gone, now there are 8 electrons on the outermost shell, and sodium becomes stable, it becomes Na+, because it removed 1 electron. And now it has 8 electrons in the outermost shell. When atoms interact to form chemical bond, only electrons in the outermost energy level of an atom are involved, right? Now, when we write this electron configuration, in here, when sodium is sodium, the outermost energy level is 3. So it is the electrons on this level that are involved in bond formation, right? The electrons in outermost energy level of an atom which are involved in chemical bonding are known as valence electrons. Now this electron, so sodium has 1 valence electron because this is involved in chemical bonding. 2 is 1, right? So there it has 1 valence electron. 3 is 1. Is it clear to you? Valence electrons? So when you write the electron configuration of sodium, the outermost electron shell of sodium, right? Nothing has happened. Sodium. The outermost level is 3. How many electrons are there in the energy level 3?
1.
1. So the valence electron, the number of valence electrons of sodium is 1. The number of valence electrons of sodium is 1. Okay. So only, okay, why do atoms of different elements react? Continuation. Only noble gases in group 8A periodic table, the last group 8A, has noble gases. So we have helium, neon, argon, krypton, xenon, likewise. So they have a full outermost shell. They are stable as individual atoms, right? So they have full outermost shell, and because of that, they are very stable. So noble gases do not readily react to form bonds as they have stable electron configurations. So if we take helium, the electron configuration is 1s2. So what is the maximum number of electrons that energy level 1 can have? What is the maximum number of electrons that energy level 1 can have?
2.
2, right. Correct. So now in this case, helium has 2 electrons on energy level 1. That means the outermost shell is complete. It is full. Right? And because of that, helium atoms are stable. They don't have to react with other elements to become stable because they are already stable. So if we take argon, 1s2, 2s2, 2p6, 3s2, 3p6. The outermost shell, outermost energy level is 3. And these main groups, S and P, are filled. S and P are filled. Main orbitals S2 and P6 are filled. So that means it has 8 electrons in the outermost shell. 8 electrons in the outermost shell, and because of that, argon is very stable. It doesn't have to react with other atoms. Is this clear to you now? Helium has 2 electrons. Of course, energy level 1 can have 2 electrons maximum. So it is stable. If we take neon, what comes below helium is neon. It has the electron configuration of 1s2, 2s2, and 2p6, right? In that case also, the outermost electron shell, 2s2 and 2p6, if we consider these orbitals, they have like altogether 6 electrons. The outermost electron shell is complete, and because of that, neon is stable. So if we take argon, it has another shell, electron level, 2s2 and 2p6 is the electron configuration of the outermost energy level. It has 8 electrons in the outermost shell. Because of that, it is stable, argon. Now, I think we learned about the octet rule. There is a rule called the octet rule. Atoms often gain, lose, or share electrons to achieve the same number of electrons as the noble gas closest to them in the periodic table. What does it mean? So because all noble gases except helium, we learned that helium has 2 electrons. Of course, the first energy level can have a maximum of 2 electrons. Apart from helium, all other noble gases have 8 electrons on the outermost shell, right? And many atoms undergoing reactions also end up with 8 valence electrons. 8 electrons in the outermost shell. Octet rule, atoms tend to gain, lose or share electrons until they are surrounded by 8 valence electrons. Now, yes, now these are the 8A group, the noble gases, right? Helium, neon, argon, krypton, xenon, radon. Likewise, these are the noble gases. So what the octet rule says is that the other atoms try to get the electron configuration of the noble gas closest to them in the periodic table. Now, if we say take hydrogen, what is the noble gas closest to hydrogen? What is the noble gas closest to hydrogen?
Helium.
Helium, right. Helium has 2 electrons. Now, when we say hydrogen, what will hydrogen want to happen? How many electrons should it gain to become helium? To have electron configuration like helium? Another electron, right? Have you, so I'm sure you know hydrogen gas. Hydrogen gas. So what happens is now hydrogen gas is H2. Hydrogen gas, you know about H2. Hydrogen gas. So what happens is that now hydrogen has 1 electron. Hydrogen has 1 electron. But to get the electron configuration of helium, it should have another electron. So what it does is that it reacts with another hydrogen. So this hydrogen also has an electron, right? Now these 2 hydrogens have shared 2 electrons. So if we take this hydrogen, it has 2 electrons around it. Likewise, if you take this hydrogen, it has 2 electrons around it. So both the hydrogen atoms are happy, right? So if we take lithium, what is the What is the noble gas closest to lithium? What is the noble gas closest to lithium? Neon. No, helium is the correct answer because if we write the electron configuration, 1s1, this is 1s2, lithium is 1s2, 2s1. So if it has to go to neon, it has to go through 2s2, 2s3, 2s4, 2s5 likewise. So the closest noble atom to lithium is helium. So what will lithium do to have the electron configuration of helium? What will it do? What will lithium do to have an electron configuration like helium? Now forget about hydrogen.
Madam, lithium wants to 1 electron for 2s1.
Yes, but what we have to remember is that filling 2s2 is doesn't mean that the outermost electron level is complete. The second energy level has P3 as well, 2p3. There are three p orbitals in the second electron shell level. So to have a complete second electron level, the electron configuration should be 2s2 and 2p6. Can lithium achieve it easily? 2s2 and 2p3, 2p6. I hope you can understand what I'm saying. Now, the first orbital, the full electron shell is 2s2. The maximum number of electrons that the first shell can have is 2. But when it comes to the second electron level, right? When it comes to the second electron level, when it comes to the second electron level, 2s2, the full outer shell is 2s2 and 2p6. 2p6, right? So lithium, what is easier for lithium to achieve? So just filling 2s2 is not enough because it doesn't represent a complete outermost shell.
Lithium releases 1 electron.
Yes, it loses 1 electron and then it can have this electron configuration, the electron configuration of helium. So very often we see lithium plus after losing 1 electron, right? So if I say oxygen, So what will be the easier thing to do for oxygen to have a complete outermost shell, to have 8 electrons in the outermost shell? What will it do? What is the easier way to achieve a complete outermost shell for oxygen?
Gain 1 electron.
If oxygen gains 1 electron, it will have the electron configuration of fluorine. Fluorine is not a noble gas. What can it do?
Getting 2 electrons.
Yes, it can get 2 electrons. So then it will have the electron configuration of neon. So that is what oxygen usually does. It either gets 2 electrons to become the oxide ion. If we say oxide, the electron configuration is this. 2 negative electrons, negatively charged electrons. And now oxygen has obtained 2 negatively charged electrons. So we say oxide ion. Or else, without completely obtaining 2 electrons, it can share electrons so that the outermost shell will have 8 electrons. The electron configuration of neon is achieved. That can happen. We will see examples in the coming slides. And now tell me chlorine. What will it do? Chlorine. What will it do to become stable?
It will take 1 electron.
Right, it will take 1 electron. If it does, it will have the electron configuration of argon, which is noble gas. That is true. And how about magnesium? What will it do? Magnesium?
Releasing 2 electrons and
Right.
getting the neon.
Yes, correct, very correct. So it can, rather than getting 6 electrons and getting the electron configuration of argon, so it has to gain 6 electrons. That is difficult. So it can easily lose 2 electrons and get the electron configuration of neon. So now I see that you have very well understood what happens, why chemical different atoms of elements react. You know why they react. So you have a thorough understanding of, of it. Now let's learn about Lewis dot symbols. To keep track of valence electrons in a chemical reactions, keep track of valence electrons, and to make sure that the total number of electrons, the total number doesn't change, chemists use a system of dots introduced by Lewis, called Lewis dot symbols. Lewis dot symbol consists of a symbol of an element and 1 dot for each valence electron in an atom of the element. transition metals, D block. So you learned about D block yesterday. We are not going to have a deep like it I mean we talk about transition metals such as iron and copper, but we are not going to learn a lot about transition metals. We are looking at principles. Anyway, D block lanthanides and actinides have incompletely filled inner shells, right? And because of that, we are not using Lewis dot symbols for transition metals and lanthanides and actinides. We are looking at elements of the major groups. Yes, Lewis dot symbol only written for representative elements S and P block. Dots are placed on the four sides of the atomic symbol. So we will look at an example very quickly. Each side can accommodate up to 2 electrodes. Right, so here is one example. There are 2 examples. Right, so dots are never paired unless more than 4%. Right, so if we take carbon, the atomic number is 6. The atomic number is 6. It has like it has 1s2, 2s2 and 2p2, right? Electron configuration is this. One is 2, 2s2 and 2p2. This is the electron configuration, right? So in the outermost shell, it has 4 electrons. 4 electrons. But it can accommodate up to 8 electrons. So when we write the Lewis dot symbol, we actually first put 1 electron on one side. So the top 1 electron, on the right hand side 1 electron, bottom 1 electron, and the left hand side 1 electron. Because it has 4 valence electrons. 4 valence electrons. Right? 4 valence electrons. We do not couple. They are unpaired electrons. Okay? And then, but when it comes to chlorine, it has 7 electrons on the outermost shell. 7 electrons in the outermost shell. So we put just one electron. First we put 1 electron. 1 electron, 1, 2, 3, 4, 5, 6, 7. Right? So there are 3 pairs of electrons and 1 unpaired electrons. This is how you draw Lewis dot symbols. Is this clear to you? Shall we look at more examples?
Okay, ma'am.
Yes, I think that's right. Can you see the slide? Chlorine, carbon.
Yes, ma'am.
Yes, madam.
You can see, right? Yes, these are some examples. These are the different groups and these are the periods. So when we take lithium, lithium has this electron configuration of 1s2, 2s, 1s2, 2s1, 2s1, right? So it, as you very correctly mentioned previously, it loses one electron to become lithium plus. But now we are looking at the Lewis dot symbols. The outermost electron shell is 1, 2, S1. So the number of valence electrons is 1. So we have this chemical symbol, lithium, and we put one dot because it has 1 valence electrons. So if you take beryllium, that is in the 2A group, the electron configuration is 2s2. 2s2, it has two electrons in the outermost shell. So 2 electrons, 2 valence electrons, so unpaired. When it comes boron, it has 3 unpaired, it has the electron configuration of 2s2, 2p1. So that means it has 3 valence electrons. So we keep 3 dots. So we looked at the case of carbon. It has the electron configuration of 2s2, 2p2, 4 electrons unpaired. But when it comes to nitrogen, there are 5 electrons, 5 valence electrons. So this is how we measure, because we have to pair 1 electron to accommodate the 5 electrons around nitrogen. So oxygen, 6 electrons, fluorine, 7 electrons, neon, 8 electrons. Right, so I think now you know how to represent atoms of different elements using the Lewis dot symbol. Is it clear to you?
Yes, ma'am.
Right. So now we are going to learn about different types of chemical bonding. Chemical bonds. There are many different types of bonds. One is ionic bond, 2 is covalent, coordinate covalent, and metallic bonds. So these are the different types of bonds that we are going to discuss today. Ionic bond. Nucleus of an atom is unchanged in ordinary chemical processes. So we know that an atom has a nucleus and electrons around it. The nucleus does not change. Only the electrons are involved in chemical bonding. But atoms can readily gain or lose electrons. The electrons are removed or added to a neutral atom. Okay, if the electrons are removed or added to a neutral atom, then charged particle or an ion is formed. So we know that when sodium loses an electron, it becomes sodium plus ion. So when chlorine gains one electron, it becomes chloride ion. Likewise. An ion with a net positive charge is called a cation, like sodium, and ion with a net negative charge is called an anion. So net charge of an ion is represented by superscripts. Superscripts, you know what superscripts are, right? Superscripts can have udin තියෙන්නේ. So if I'm sure you know what superscripts are. Then මෙහෙම තියෙන්නේ sodium. මෙහෙම superscript කියන්නේ මෙහෙම උඩින් දාන්නේ superscript. Right? So we show the charge using superscript. So if we say oxygen 2 minus, those are superscripts. In general, metal atoms such as sodium, magnesium, likewise, they tend to lose electrons, and non-metal atoms tend to gain electrons. Non-metal atoms such as oxygen, chlorine, fluorine, they are non-metals. They gain electrons to become negatively charged, some they participate in covalent bonds as well, but we can come to it later. The metal atoms lose electrons, non-metal atoms gain electrons. Here, non-metals, metals, sodium, potassium, magnesium, iron, copper, things like that are metals. And then non-metals, oxygen, nitrogen, oxygen, fluorine, chlorine, sulfur, likewise. And ionic compounds. Ions form when one or more electrons transfer from one atom to another. When there is a complete transfer of electrons from one atom to another, when there's a complete transfer, we get ionic compounds. When there's a complete transfer. So when we take sodium chloride, from sodium an electron is completely transferred to chlorine. Right? So then we have sodium plus and chlorine minus. And between sodium plus and chlorine minus, that is chloride, there are electrostatic attractions. And that is what makes an ionic bond. So once form positive and negative ions, they attract together to form ionic compound. Right? So ionic compounds have a positively charged ion or ions and negatively charged ions. Usually, ionic compounds are combinations of metals and non-metals. So calcium, sodium chloride, lithium fluoride, calcium oxide are some examples of ionic compounds. Ionic bond result from the transfer of electrons from one element to another. The opposite charges attract together to form ionic bonds. The electrostatic force is the electrostatic force that holds the two ions together. So that is known as an ionic bond. So let's look at the Lewis dot symbols. Lewis dot symbols, sodium, chlorine, the two atoms, right, can be connected like this, and then sodium loses the outermost electron, so it becomes sodium plus. Chloride gains 1 electron from sodium. So around chlorine, we have to indicate 8 electrons with the one that was obtained from sodium. So it becomes chloride, chlorine minus. Right? So this is how we can show the ionic bond formation using Lewis dot symbols. So when it comes to magnesium oxide, right? So magnesium, the oxygen has 6 electrons. To complete, to make the outermost electron shell full, it needs the 2 electrons of magnesium. So oxygen will have 8 electrons around it, and magnesium will form magnesium 2 plus. So this becomes 2 minus, because originally when it is neutral, it had only 6 electrons. Now it has 8. So this becomes 2 minus. Ionic compounds are stable due to the interaction between ions of unlike charge. That means positive and negative, unlike charge. So they form these solid arrays or lattices, right? So this is a picture of the sodium chloride lattice. So in the lattice, one sodium is surrounded by 6 chloride atoms. Not very important, but we can see that. And one sodium ion is surrounded by 6 sodium ions. It exists as a lattice, right? So there are electrostatic attractions between the positive and negative charges. It exists as a lattice. Now let's look at the covalent bond. Covalent bond. Atoms might acquire noble gas electron configuration by sharing electrons. Now, when we talked about the ionic bonds, we are talking about losing electrons and gaining electrons to form ions. But that is not the only way of forming bonds between atoms. We can have covalent bonds too. In covalent bond formation, what happens is that electrons are shared with other atoms. The chemical bond formed by sharing a pair of electrons is called a covalent bond. Right? Covalent compounds are compounds that contain only covalent bonds. So, examples are hydrogen, water, fluorine. I showed you how hydrogen shares electrons to form the hydrogen gas, H2. Right? I showed you how hydrogen has 1 electron. Another hydrogen, if we take it, has 1 electron. So these 2 electrons can be shared between 2 hydrogen atoms. In that case, we have H2 molecule. Molecules. When 2 or more atoms of the same element are bonded together by sharing electrons, form molecules. So these are examples of diatomic molecules. Molecules made up of 2 atoms. So hydrogen, we talked about hydrogen, nitrogen, oxygen, fluorine, chlorine. These are examples of diatomic molecules. So the same atoms of the same element can react with each other. Likewise, atoms of two or more elements can react. So, right? So then we have molecular compounds. They are generally composed of non-metals only. So if we take these compounds, water, H2O, methane, CH4, ammonia, NH3. Now you can see that there are atoms of different elements, right? So that can also happen. Lewis structure. The formation of covalent bonds can be represented using Lewis structures. So we showed the formation of ionic bonds using Lewis structures. Likewise, we can show the formation of covalent bonds using Lewis structures. A Lewis structure is a representation of covalent bonding in which shared electron pairs are shown either as lines or pairs of dots between two atoms, and lone pairs are shown as pairs of dots on individual atoms. So we will look at some examples so that it will be clearer to you. Only valence electrons are shown in the Lewis structure, electrons of the outermost shell, valence electrons. Lone pairs, that means unpaired electrons. Pairs of valence electrons that are not involved in covalent bond formation. Two unpaired electrons that are not involved in forming covalent bonds are called lone pairs. So we will look at fluorine. Fluorine is a group 7 element. So it has 7 electrons or 7 valence electrons. And if we take the other atom, it also has 7 electrons. But if it shares 2 electrons, that is one from this fluorine and one from this fluorine, if these 2 electrons are shared, then this fluorine has 8 electrons. This fluorine has 8 electrons around it, and this fluorine has 8 electrons. So these 2 electrons are shared. So that is called a covalent bond, and we can denote this bond using a line that is easier, easily understandable. Right? If we do that, that's clearer. Atoms can form different types of covalent bonds. Single bonds. So in the case of fluorine, we saw a single bond between fluorine and fluorine. 2 atoms are held together by 1 electron pair. There can be multiple bonds as well. In this case, 2 atoms share 2 or more pairs of electrons. 2 or more pairs of electrons. Right? So that is called a multiple bond. If we are talking about 2 or more bonds, multiple bonds. So we will look at an example, carbon dioxide. Right? So oxygen has, so the chemical formula is what? CO2, carbon dioxide. It's CO2. This is carbon dioxide. So 2 oxygen atoms and 1 carbon. So oxygen has 6 valence electrons. So there is another oxygen that has 6 valence electrons. And carbon has only 4 valence electrons. So this 6, if it is 8, the electron configuration of the outermost shell of oxygen will be full. And yeah, so what it does is with this oxygen, 2 electrons are shared. That means 2 from oxygen and 2 from oxygen, 2 from carbon and 2 from this oxygen. Right? So in oxygen, there are 2 lone pairs. So these 2 electrons are there. So from carbon, 2 electrons come. Right? The same thing happens with the other oxygen and carbon. Right? So because now it has 2 unpaired electrons, and carbon also has 2 unpaired electrons. So these 4 electrons are shared. So it has a double bond here, a double bond here, 2 double bonds. So these are multiple bonds. Right? So when it comes to so oxygen also, now 6 electrons and 6 electrons. This oxygen needs 2 electrons and this oxygen needs 2 electrons. So if they share 2 electrons from each atom, then there will be a double bond between oxygen, the 2 oxygen atoms, and there will be 8 electrons around each oxygen. So that is how multiple bonds are formed. Is there any question? Okay. Now, right, we will have a 10-minute break. 10-minute break. Now it's 10:47. Shall we meet at 11? Slightly greater than 10 minutes. So we'll meet again at 11.
Okay, miss.
Right.
Okay, madam.
Yes, ma'am. Yes, I'm back again. So yeah, so you had no questions here. Right, so we will go to the next. Yes, we have now come to part 2 on chemical bonding. Now, Right. So this chemical bonding, it happens, yes, it can be explained using bond polarity and electronegativity. So electron pairs shared between two different atoms are usually not shared equally. Now, if we take, there are two extremes. One is one is is when the electron cloud is symmetrical. That happens when the bond is between the same two atoms. That is chlorine-chlorine. If it is between two chlorine atoms, if it now you know what electronegativity is, right? So if we take two chlorine atoms, the electronegativity is the same, and because of that, the two electrons are shared equally between the two atoms, right? So similarly, if we take fluorine, F2, two atoms, F2, F and F, so the electrons are shared equally between the two atoms. So that is one extreme, bonding between two identical atoms. Electron pairs are equally shared. The other extreme is that the electron is completely donated to the other atom. So when we say sodium chloride, sodium plus becomes like it plus, it gets rid of the electron completely, and chlorine obtains that electron, so it owns that electron now, chlorine. There's an electron transfer. That is the other extreme. Usually, what we see is something in between these two extremes. Bonding occurring in most covalent substances falls somewhere in between these two extremes. I hope you can see the slides.
Yes, madam.
Then concept of bond polarity is useful in describing the sharing of electrons between atoms. So there are non-polar covalent bonds. Non-polar, so as I mentioned previously, if the bond is between is between identical atoms, is one in which electrons are shared equally between two atoms. So those are non-polar covalent atoms. And there are polar covalent bonds. That is when one atom has a higher electronegativity. That means it exerts a greater attraction for bonding electrons than the other. An example is hydrogen chloride. Chlorine has a higher electronegativity than hydrogen, and because of that, the electron cloud is not symmetrical on the molecule. If the difference in relative ability to attract electrons is large enough, if the electronegativity is very different, if there's a huge gap, then an ionic bond is formed. So I'm giving examples. Chlorine, chlorine, Cl2. A non-polar covalent bond is formed. Bonding electrons are shared equally between the two atoms. And here, hydrogen chloride, as I mentioned previously, this is a polar covalent bond. The bonding electrons are shared unequally. There's a partial charge on the atoms. Now, because the electron cloud is distorted, there is a partial charge because the electrons are now located more around chlorine. Now chlorine has a partial negative charge, delta negative, partially negative, delta negative. And hydrogen now has a partial positive charge because the electron cloud is now towards chlorine. Because of that, hydrogen has a partial positive charge. We call it delta positive, right? And this is the third one, ionic bond. Completely, the electron is donated to the other atom, right? Full charges on resulting ions. The property that helps to distinguish a non-polar covalent bond from a polar covalent bond is electronegativity. So you, I think, yesterday learned about electronegativity. It's a measure of the ability of an atom that is bonded to another atom to attract the electrons in the chemical bond towards it, to attract the bonding electron towards it, to attract the bonding electrons towards it. That is the electronegativity of an atom. Electronegativity of an atom in a molecule is related to its ionization energy and electron affinity. Also, you learned about these things yesterday. So these are properties of isolated atoms, right? These are properties of ionization energy and electron affinity are properties of isolated atoms. So ionization energy is the energy required to remove an electron from a gaseous atom when the atom is in its ground state. Now, you don't have to worry much about it. I think it's important that you learn the definition, but what you have to keep in mind is that how easy it is for the atom to remove its outermost electron is given by this ionization energy. If the energy that is required to remove an atom is small, if it is small, that means it can form positive ions very easily, right? The energy required to remove an electron. If we have to give only a small amount of energy, that is good because then it can form a positively charged ion very easily. So measures how strongly an atom holds its electron. If ionization energy is high, doesn't look, yes. If ionization energy is high, if it is low, easily positive ions are formed. If the ionization energy is high, in those cases, they don't lose electrons easily. For example, if we take something like did you learn about these electronegativity, ionization energy, and these things in the last yesterday? Did you learn about these things? Did you learn about these things? No? Okay, in that case now, yes, it's important that you know the definition. It's very important that you know the definition. You learned, right? So electron affinity is a measure of how strongly an atom attracts additional electrons. Electron affinity is how strongly one atom can attract additional electrons. Electron affinity, right? Not this is electronegativity is something else. Electronegativity is, so in electronegativity we are talking about the bonding electrons. How well an atom can attract the bonding electrons, that is electronegativity. Electron affinity is how strongly an atom attracts additional electrons. So you isolate an atom and determines how strongly it can attract electrons, right? So electroaffinity and electronegativity are two different things. We are looking at two different things, right? If electroaffinity is high, it tends to pick up electrons easily. It tends to pick up electrons easily. So something like fluorine, it should have very high electron affinity. It can pick up electrons very easily, forming a negatively charged ion. Atom with high electron affinity and high ionization energy, right? High electron affinity means that atom can can attract electrons very easily, an atom. High ionization energy means if we take an atom, it's very difficult to remove an electron from it. That's if it has high ionization energy. It's very difficult because we have to give a lot of energy if we want to remove an electron from that atom. In that case, right, if an atom has very high electron affinity, that means easy to attract the electrons, and high ionization energy. Like if it needs very high energy to lose electrons, then such atoms have high electronegativity. That means when they're forming bonds in the molecule, these atoms with high electronegativity attract bonding electrons very easily. Atom with low electron affinity and low ionization energy, these atoms have low electronegativity. Low electron affinity, that means they cannot obtain electrons easily, they cannot. And low ionization energy, only a small amount of energy is needed to get rid of electrons. So such atoms usually have low electronegativities, such as sodium. So if we take this trend, if we take the atomic size decreases along a period. So we know, I think you knew, you learnt, it decreases along a period, atomic size. Increases down a group, increases. So more shells are added, so the size increases. Here, the nuclear charge increases, and because of that, the attractive force towards the electrons on the outermost shell is more. So because of that, decreases a period. Ionization energy, electron affinity, electronegativity. Decrease down a group. Why is that? Decrease down a group because the size is now bigger. Because of that, the attraction of the nucleus towards the outermost electrons is very less, and because of that, easily electrons can be removed. Ionization energy decreases. Electron affinity and electronegativity also decrease because now the effect of the nucleus on the outermost shell is very low because the size increases. So increase along the period, ionization energy, electron affinity, electronegativity, it increases along the period. So I'm sure you know the reason. If you don't know the reason, please ask me. So difference in electronegativity between two atoms can be used to gauge the polarity of the bonding between them. So this is a repetition of the previously explained slide. So again, I tell you now the atoms are identical, electronegativities are identical, and because of that, the electrons are shared equally in the molecule around these two atoms. Here, the electronegativity is different. Chlorine has much higher electronegativity than hydrogen. Because of that, the electron cloud lies more towards chlorine. So now there's a partial positive charge on hydrogen and partial negative charge on chlorine. Here is the other extreme. That an electron is completely transferred from sodium to chlorine. So there's a positively charged ion and a negatively charged ion formed. So this is an ionic bond. So this is explained further. Right. So I explain these things, right? Greater the difference of electronegativity, the electronegativity is different, right? Between these two. Yes. Greater the difference in electronegativity between two atoms, the more polar their bond. Right? The polarity is determined by the difference of the electronegativities of the two atoms. This is the electronegativity is like the difference in electronegativity is very high, and because of that, this bond is very polar. So that leads to a complete, now if we take sodium chloride, it leads to a complete transfer of the valence electrons. Right? Now we know about an ionic bond and a covalent bond. We know about symmetrical covalent bonds, and then we know about polar covalent bonds. Another type of covalent bonds is coordinate covalent bond. Here what happens is Okay. What I was saying is that there are ionic bonds, there are covalent bonds, there are polar covalent bonds, and there is another type of covalent bonds, and we call it coordinate covalent bonds. So that is a covalent bond in which one atom of the atoms donated, one of the atoms donates both electrons. So one example is given here. If we take ammonia, right? Ammonia, it has 3 bonds and 2 electrons. It is happy because it has 1, 2, 3, 4, 5, 6, 7, 8 electrons around it, right? Nitrogen. Now each bond represents 2 electrons, 1, 2, 3, 4, 5, 6, 7, 8 electrons. Now here, what this lone pair of electrons can be used is to form a coordinate bond between H plus, right? So no electrons, has empty orbitals. Hydrogen has no electrons, now has an empty orbital. So what nitrogen can do is to donate these 2 electrons to hydrogen. Donate these 2 electrons. So the sharing electrons come from a single atom, right? Now, even though we say donate, it is not 100% given to hydrogen. It is the 2 electrons, the lone pairs are shared between nitrogen and hydrogen. Okay, these 2 electrons are shared between nitrogen and hydrogen. So we denote it by an arrow. So it should come in a bracket and there's a net positive charge. Because here, hydrogen, there was no electrons. So the positively charged ion was incorporated. Because of that, this whole ion, this ammonium ion, has a positive charge. This is an example of a coordinate covalent bond. Another example is given here, 2 examples actually. Ammonia and boron, trifluoroboron, boron fluoride, trifluorobromine actually. It is trifluorobromine and ammonia. In here, boron has only 6 electrons around it. 1, 2, 3, 4, 5, 6 electrons. Nitrogen has 8 electrons. So what can be done is that these 2 electrons can be shared between nitrogen and boron. Now there are 8 electrons around boron and 8 electrons around nitrogen. Right, so this is a coordinate bond and we can denote it using an arrow. Here, when when hydronium ions are formed, this is a water molecule. So it has, oxygen has 8 electrons around it. 1, 2, 3, 4, 5, 6, 7, 8. It has 2 lone pairs. So a hydrogen atom, hydrogen ion, hydride ion. Yes, this should be H plus. This should be H plus, right? This is H plus, and this should be also plus. Right? Coordinate bond formed in hydronium ion. A lone pair can be given to the hydrogen ion, and then there will be a there are errors in this diagram. There are errors. Now here there should be 2 electrons to 2 electrons. 1, 2, 3, 4, 5, 6, 7, 8. Right. Does it make sense? Because the other lone pair should be there. 2 hydrogen, 2 bonds between oxygen and hydrogen. 1, 2, 3, 4, 5, 6, 7, 8. Does it make sense? Which part did you not understand? Okay, I think you have understood. So if you have questions, please ask. And then we have this then we have these metallic bonds, such as these are the kinds of bonds that we see in iron, copper, and other metals, aluminium, like other metals, right? So in this case, what happens is that now, so these are metals, right? Easily, electrons of the outermost shell, electrons are easily removed. Electrons are easily removed from these metals, metal atoms. So now it is like this. There is a lattice of positively charged ions and electrons. Now there are electrons that are removed from the atoms and they go here and there. The electrons, they travel. It is like a sea of electrons in which there is a lattice of positively charged ions. There are electrostatic attractions between the electrons and the positively charged ions, metal ions, right? So these bonds hold the atoms together. Metallic bonds are the forces of attraction between the free floating valence electrons. These electrons go here and there, and the positively charged metal ions. Okay. The metallic bond. Metals like a lattice, and then there are electrons. Now we talked about intramolecular forces, especially these covalent bonds and coordinate covalent bonds are intramolecular, that is inside the molecule. Now we are going to talk about intermolecular forces. Intermolecular forces. That means among molecules, between molecules, intermolecular. Intermolecular forces are primarily responsible for the bulk properties of matter, such as boiling point, melting point. So now, yes, for example, now boiling point. If we take, no, that's okay. It's okay. Now, boiling point. So when water boils, what happens is intermolecular forces between among water molecules break, and those water molecules then go to the vapor phase. So intermolecular forces should be broken for molecular water molecules to go into the vapor phase. So if the so if we take different molecules, if the intermolecular forces are very strong, then the boiling point becomes very high because they need a lot of energy to break the bonds among molecules. If the intermolecular forces are low, then boiling or converting liquid water into liquid compounds into vapor will happen fast if at a low temperature, if the intermolecular forces are not that strong, are weak. Intramolecular hold atoms together in a molecule and stabilize individual molecules. Intermolecular forces are molecular forces that exist among molecules, and they are weaker than intramolecular forces. So there are different types of intermolecular forces. We collectively call them van der Waals forces. Van der Waals. Dipole forces are there, dipole-induced dipole forces, and dispersion forces. Now let's look at each of these intermolecular forces. Dipole forces. Now remember hydrogen chloride, the hydrogen chloride HCl, where the electronegativity of the two atoms is very different. So in that case, hydrogen had a delta positive charge and chlorine had a delta negative charge. So this is an example. Now, of course, this doesn't show the distortion of the electron cloud, but that's okay. So there is a partial positive charge here and partial negative charge here. Here also there's a partial positive charge here and partial negative charge here. So these partial negative charges and partial positive charges are attracted to each other. There is an attraction, right? So this is a kind of intermolecular force. this is a molecule, this is a molecule, and intermolecule. In between these two molecules exist this type of attraction. This is called dipole-dipole forces. Dipole-dipole forces. Now there is this ion-induced dipole. Ion dipole force. So what here is ion dipole force. So now think of this molecule as a polar molecule. There's a partial positive charge here and partial negative charge here. The partial positive charge is attracted to anions, which are negatively charged. These partial negative charges are attracted to the cations. This type of intermolecular bonds is called ion dipole force. Right? And there is this induced dipole. Induced dipole. That is the separation of a positive and negative charges of an atom or non-polar molecule is due to the proximity of an ion or polar molecule. Right? So let's have a look at this. Here, this is a positive charge. Then what can happen to this? This oxygen molecule, which is non-polar. What can happen? This is slightly wrong actually here. What actually should happen is this. Positive. This should be negative. Right here, what will happen is in the presence of a positive charge, then the cloud will go towards that direction, electron cloud. So there will be a partial negative charge here and a partial positive charge here, because electron cloud will shift towards the positive charge. Right? So that is called an ion-induced dipole. There is an induced dipole, right? The dipole was not originally there. Because of the presence of these positive charge, the dipole was induced. Prayer කරලා තියෙන්නේ කියන එක. මේ වෙලාවෙ ඇති වුණ දෙයක්. Now here, in the previous case, an ion, in that case Fe2 plus, ferrous ion, was the cause to induce a dipole, ion-induced dipole. Here, dipole-induced dipole attractions are also there. So what happens here is this. Now there is a dipole here. There's a permanent dipole. The molecule, there's a partial negative charge on oxygen and partial positive charge on hydrogen because of the difference of the electronegativities. Now there's a permanent dipole here. So when it goes close to something like oxygen molecule where there is no dipole, right? Initially there was no dipole, but now on the approach of this permanent dipole, then a dipole is induced. Because this is negatively charged here, there's a partial negative charge here, then electrons move towards the other oxygen, which is farther from the water molecule. The electron cloud moves away. Now there's a partial positive charge here and a partial negative charge here. Right? Because minus negative attracts positive, right? So this tries to be positive because there's a dense electron cloud here. The electrons go towards the other oxygen atom, which is away from the water molecule. So that is a dipole-induced dipole interaction. Right? So we had ion-induced dipole interaction, dipole-induced dipole interaction. And now we are talking about something called dispersion forces. Dispersion forces. Attractive forces that arises as a result of temporary dipoles induced in atoms or molecules. Temporary dipoles induced in atoms or molecules. Now here, assume that these molecules are made of identical atoms. Now initially, there was no distortion in the electron cloud. There was no distortion in the electron cloud. But if this due to some reason, if the electron cloud becomes asymmetrical, that is, if the electron cloud move towards one atom away from the other atom, now then in that case, this molecule will have a partial positive charge and partial negative charge. Because that has happened, now the other molecule also develops some distortion. Then මෙතන අපි හිතමු oxygen කියලා. Oxygen, it should be symmetrical. The cloud should be symmetrical. මොකක් හරි හේතුවකට now there is a asymmetry. Electron cloud එකක් පැත්තට ගිහිලා. Now there's a delta positive charge here and delta negative charge here. එහෙම වුණ නිසා එයා ළඟ ඉන්න molecules දැන් මෙතන partial positive නේ. එතකොට electrons මේ පැත්තට attract වෙනවා. Right? So this also becomes like develops an induced dipole. So there are attractive forces among the molecules due to this like temporary dipoles induced in atoms or molecules. So those are called dispersion forces. It's a special type of, what is it? Hydrogen bond. It's a special type of dipole-dipole interaction between the hydrogen atom in a polar bond, NH-OF, HF. Now in NH and OH and FH bonds, the electronegativity difference is very high. So this hydrogen and an electronegative oxygen atoms such as oxygen, nitrogen, or fluorine, right? So this is what happens. I will go to the example, then it is easier for us to understand. Now there is this water molecule. The bond between these two is hydrogen and oxygen, a polar covalent bond. The electronegativity difference is very high. The electronegativity difference is very high, and because of that, this bond is very strong, and a partial positive charge and a partial negative charge develop in this molecule. Now, when hydrogen gets closer to oxygen of another molecule, right? Now, still the electronegativity difference is very high. Even though it is in another molecule, the electronegativity difference is high, and because of that, a very strong intermolecular bond is formed, and that is called a hydrogen bond. Right? So that is all I have to cover on chapter 6. So now let's move to chapter 7.
Recording stopped. Let's have a 10-minute break and continue. A 10-minute break. Now it's 11:55, so we will start at 12:05. Okay, now we can start learning the mass relationship in chemical reactions. So, what is a dozen? What is a dozen? What is a dozen?
Number of 12, madam.
Yes, 12. Dusimak කියන්නේ අපි dozen. 12. So we can have dozen of plantains, dozen of pumpkins, dozen of eggs, dozen of bottles, and we can have dozen of people. Also, we can have what else? Dozen of caps, like anything. Dozen is a number, right? So the number is 12. Likewise, we can learn about mole. Mole is like a dozen. Mole. In a mole, there is Avogadro number of units. Avogadro number. The number is very high. It's 6.022 into 10 to the power 23. Right? So mole has an Avogadro number of entities. This Avogadro number is this. Right? So we chose this number because now you don't have to worry much about that. This is the exact number of atoms in 12 grams of C12 isotope determined experimentally. C12 was taken as the standard C12 isotope. There are other like C13, C14. These are isotopes. Samasthānika kiyanne. But the main isotope is C12. So if we take 12 grams of it and count the number of atoms, there will be an Avogadro number of atoms, that is 6.022 into 10 to the power 23. So mole is that number. So we can have a mole of oxygen molecules. We can have a mole of iron, that is iron atoms. We can have a mole of
Recording in progress.
we can have a mole of even people. So do you understand the term mole now? Is it clear to you? What is a mole? Avogadro number of entities. What is the Avogadro number? 6.022 into 10 to the power minus 10 to the power 23. What? So how did we come up to that number? Because if we take 12 grams of the carbon 12 isotope, there are Avogadro number of atoms. So mole is, if we say mole of people, that means there should be 6.022 into 10 to the power 23 people. Mole of atoms, mole of molecules. Right? So
We are going to work with moles now. I'm sure you understood. "12 grams of carbon-12 isotope," this number of atoms, so mole, 1 mole. So this many atoms, molecule, ions, etc. is 1 mole. 1 mole of hydrogen atoms contains 6.022 into 10 to the power 23 hydrogen atoms. 1 mole of sodium carbonate contains 6.022 into 10 to the power 23 sodium carbonate molecules. We don't really call this molecule. It's okay for now, formula units, but it's okay to use molecule now. 1 mole of carbon-12 has the mass of exactly 12 grams and contains 1 mole of carbon-12 has a mass of exactly 23 grams and contains 6.022 into 10 to the power 23. This is mass of carbon-12 is its smaller mass. So we will come to it very shortly. When we look at examples, we will understand this more. It will be clearer to us. Molar mass, the mass in grams of 1 mole of units, atoms, molecules, etc. of a substance. Molar mass. So we know what a mole is. So now we are going to find out what is the molar mass. So we will so we take carbon-12 atom, right? So we are going to now define an atomic mass unit. Like we have kilograms, grams. What is a gram? What is a kilogram? What is a meter? Likewise, what is a gram? How can we define what a gram is? So likewise, we are going to, what is a gram? We are going to look at atomic mass unit. That is a unit that we use to express the different masses of atoms and molecules. How many atomic mass units are there, right? Atomic mass unit. So this atomic mass unit is 1/12 of the 1/12 the mass of an carbon-12 atom. අපි carbon-12 atom එකක් අරන් ගන්නවා. ඒකේ weight එකෙන් carbon-12 atom එකේ weight එකෙන් 12න් එකට අපි කියනවා atomic mass unit එකක් කියලා. Okay, we take carbon-12 isotope, we take 1 atom and 1/12 the mass of that atom is described as an atomic mass unit.
But you don't have to worry much because we will give the atomic masses of different atoms at the exam. Right? Sodium. The atomic mass of sodium is 22.99 AMU. Now, AMU is the unit, atomic mass unit. So, we actually usually remove the decimals and we simply say 23 atomic mass units. Right? That atom, the weight of an atom is 23 AMU. So, what is the molar mass? Molar mass is that in grams. Atomic mass. If we take an atom, the mass is sodium atom, the mass is 23 AMU. If we take molar mass, that is 1 mole of sodium. If we take the molar mass, the weight is atomic mass in grams. Molar mass is 23 grams per mole, of course. 23 grams per mole, molar mass. So atomic mass is usually, the atomic mass is usually given in AMUs, 23 AMU. Molar mass is given in grams per mole. This is AMU. Molar mass is given in grams per mole. The atomic mass of an element, okay, the atomic mass of an element is equal to molar mass of that element in atom. ඒක තමයි අපි මෙතන කිව්වේ. Atomic mass of an element. ඒ කියන්නේ atomic mass එක 23 AMU. 23 AMU. ඒකම gram වලින් කිව්වහම ඒක molar mass එක වෙනවා. AMU වෙනකොට එතන grams ගත්තොත් ඒකේ තියෙනවා මවුලයක්. molar mass එක. Right? Molar mass of an element, atomic mass in AMU equals the mass number. A molar mass of an element, molar mass. If you take the number, it is equal to atomic mass in AMU. Example, we take this sodium isotope, 2311. The mass number is 23. What is the atomic mass? 23 AMU. We take the mass number 23. Mass number 23. So the atomic mass is 23 AMU. The molar mass of sodium is 23 grams. එච්චරයි පුරුදු වෙන්න තියෙන්නේ. මෙතන AMU කියනවා අපි එක atom එකකට මවුල් එකටම A ගානම gram වලින් කියනවා. Atomic mass 12, molar mass 12 grams per mole. Atomic mass මෙතන 24, molar mass 24 grams per mole. Calcium වල atomic mass එක 40, molar mass 40 grams per mole. Oxygen වල atomic mass එක 16, molar mass එක 16 grams per mole. Now there is this table. Element, atomic mass, molar mass, number of atoms. Atomic mass, if it is 1.01 AMU, molar mass is the same thing in grams per mole. Atomic mass එක හැම වෙලාවෙම අපි දෙනවා. Atomic mass එක දෙනවා. එතකොට molar mass කියන්නේ මේක කියලා ඔයගොල්ලෝ දැනගන්න ඕනේ. ඒකම grams per mole. 24.3, 24.3 grams per mole. Sodium, 23 grams per mole. The molar, if you take 1 mole, the number of atoms is this. For all other substances, compounds, molecules, the molar mass in grams is numerically equal to the formula weight, molecular weight of atomic mass. Yes, okay. So we give the molar mass or atomic mass at the exam, but you will have compounds made of different elements. In that case, we have to calculate the molar mass. Gram formula weight or gram molecular weight. We have to calculate. Here are some basic examples. Sum of the atomic masses in AMU in the mole. That's molecular weight. If we take water molecular weight. Molecular weight, there are 2 hydrogens. The atomic weight of hydrogen is 1. So 1 into 2, because there are 2 atoms. The atomic weight of oxygen is 16. 16 into 1, because there is 1 oxygen. 18 AMU. This is the molecular weight of water. The molar mass is that thing in grams per mole. Formula weight. So if we take sodium chloride, sodium, the atomic weight of sodium is 23 and the atomic weight of chlorine is 35.5. So the formula weight is 58.5. The molar mass of sodium chloride is, so now molar mass, the formula weight is given here. So we just only have to express this value in grams per mole. 1 mole weighs, the weight of 1 mole is 58.5 grams sodium chloride. This is one of the questions. In your book. Calculate the molecular weight or formula weight in each of the following substance. So can you calculate these two? So sulfur dioxide and calcium chloride. Can you calculate these two? Taking the values from here, given here. Now calculate. Did you calculate? Okay, I think all of you have done it correctly. So sulfur dioxide, I am happy that you have done it correctly. Sulfur 32 AMU, dioxide 2 oxygen 16 into 2 64, that is correct. And here calcium chloride, calcium 40, chlorine 2 chlorine atoms, 35 into 5 into 2, 35.5 into 2. The value is 111. So I'm sure you at home try to calculate everything. Yes, you've done it correctly. So yeah. Now the other thing that we will have to do, even at the exam, is to calculate the number of grams, okay, to convert weights into moles or moles into weights, and sometimes into the number of molecules or atoms or things like that. So the basic definition that we should keep in mind is this. Moles is equal to weight or mass divided by molar mass. Right? Molar mass, this is weight. So this is the basic equation, and it is very important that you know these equations, and it's very important that you're able to use this equation. This is very important because definitely at the exam, you will have to use this equation. So, moles, weight divided by molar mass. So molar mass of sodium is 23. Okay. The question is this. Calculate the number of grams of sodium in 12.3 moles of sodium. Oh. The number of moles is here. What is the number of moles? What do you have to put here?
12.3.
Yes, 12.3 moles. So we have to calculate the weight, right? Calculate the number of grams. Means we have to give the weight. So what is the value that we have to put here? The molar mass. What is the molar mass?
23 grams per mole.
Right, 23 grams per mole. I think you can, now this is clear to you. I think I'm happy here. Moles ගාන අපිට මෙතන දීලා තියෙනවා. 12.3 moles. සමානයි. අපි අහන්නේ weight එක. නේ weight එක අහන්නේ. Number of grams. එතකොට මෙතන molar mass එක අපි දන්නවා atomic mass unit, atomic mass එක grams per mole වලින් දුන්න ගමන් ඒක molar mass එක. මෙතන 23යි AMU අපි කියන්නේ 23යි. ඒ කියන්නේ 23ක් මවුලයක තියෙන weight එක මෙච්චර. මවුලයක weight එක මෙච්චරයි. දැන් මොකද කරන්න පුළුවන් අපිට? weight එක හොයන්න නම් මොකද අපි කරන්නේ?
12.3 multiplied by 23.
Hurry. Right. That is exactly what we have to do. 12.3 moles should be multiplied by 23 grams per mole. So what is the result?
Two hundred and 82.9.
282. Right, 282.9. That is the answer. So what is the amount of atoms in 12.3 moles? What is the number of atoms in 12.3 moles? What is it? What is the number of atoms in 12.3?
6.022 into 23 times of 10. It's Avogadro number, madam.
Avogadro number is multiplied by 12.3, right? Yes. Because now there is only 12.3 moles. In one mole, there are 6.022 into 10 to the power 23 in one mole. When it comes to 12.3 moles, how much? We have to multiply the Avogadro number by the number of moles, right? Then එක මෝල් එක තියෙන්නේ කොච්චරද? 0.22 නේ. එක මෝල් එක තියෙන්නේ මෙච්චරයි. එහෙමනම් 12.3 මෝල් එක කොච්චරද? එක මෝල් එක තියෙන්නේ මේක. එහෙනම් 12.3 moles වල කොච්චර? මෙහෙම නේද වෙන්න ඕනේ. Am I correct? The number of atoms.
What is the answer, ma'am?
I'm sorry?
What is the answer?
You have to multiply and see. Forget about 10 to the power 23. Multiply 6.022 by 12.3. What is the answer that you get? Right. That is the answer you get. So it is something like 7.4 roughly 7.4 into 10 to the power 24. Something like that, closer to that value. 7.4 into 10 to the power 23. Something like that. Did you get the same answer?
Can you do it for us, ma'am?
This is it. 6.022 into 10 to the power 23. That is for 1 mole. Then 12.3 moles. The answer is, so if we forget about 23, the answer is 74 something. Right? So as your friends have indicated, 74.0706. So let's forget about the decimal points. I think you can see this. Right? Okay, 74.0706 into 10 to the power 23. Then you can have the decimal place here. Then it will be 7.4 into 10 to the power 24. Even if you write this answer, we can consider it correct. Right. There are some review questions. Molar mass of atomic weight of helium is given. Now, how many moles of helium atom are in 6.64 grams of helium? The molar mass, atomic mass is given. So the molar mass is 4 grams per mole. The number of moles, what should be divided by what? number of moles. To get the number of moles, මතකද අර equation එක? This one. Weight divided by molar mass. Weight divided by molar mass. ඒක තමයි ගන්න ඕනේ. Weight is given here. Weight divided by molar mass. Molar mass. And when you divide the mass by molar mass, you get the number of moles. Another question is how many grams of zinc are in this many moles of zinc? How many grams of zinc? Then what do we put? මොකක්ද අපි පාවිච්චි කරන්න ඕනේ? How many grams කියලා තියෙන්නේ? The amount of moles is given here. I'll shorten the equation and give it to you. The number of moles is equal to the weight or mass divided by molecular weight. Yeah. Right. That's correct. Then the number of moles we know 0.356. The molar mass is given. So how many grams? We have to multiply the number of moles by the molecular weight. Not the molecular weight here, atomic weight. Molar mass. Right? So when you do a few examples, you will understand it better. Even if I do all the problems here, you won't, get the practice. Can you try to solve this problem? How many atoms are there in 16.3 grams of sulfur?
What is the easier way to do this? Can you tell me the steps? What is the first thing that you would do? Forget about the answer here. What is the first thing that you should do?
Need to find how many moles in 16.3 grams.
Exactly.
Then it should be multiplied by the Avogadro number.
Right, right. That's correct. That's the easier way to do it. Right. Yes. Here sometimes, now here I think you will do the problem. The now here this is not this is actually straightforward, but you'll have to calculate the molar mass. The atomic mass is given. Atomic mass of carbon and the atomic mass of hydrogen are given. So you first of all, we have to calculate the molecular weight and then use that molecular weight that we calculated to solve the problem. Right? So things like that will have to, I mean, you'll have to do things like that at the exam. Okay, shall we
Recording stopped.
shall we have the lunch break now? Half an hour? Will that be enough?
Excuse me, ma'am.
Yeah?
You say about previous slide.
Yeah. What is your question?
What did you say about previous slide? I didn't hear you properly.
I told you that sometimes we might not give directly the, I mean, we might not ask you to calculate using single elements, sulfur or zinc or sodium or things like that. Sometimes we might give you molecules such as methane, ammonia, and things like that. But we will be giving you the atomic mass units, the atomic weight will be given. You will have to calculate the molecular weights using the atomic weights.
Okay, ma'am.
Right. So then we will have our lunch break at 1:30. Now it's 12:52. We will meet at 1:30.
Okay, madam.
Molecules or atoms or substances react with each other to form products. Reactants form products. So actually, what is the correct way of expressing what happens actually in a chemical reaction? Now, chemists have devised a standard way to represent the reactions by using chemical equations. So, chemical equations consist of chemical symbols, in this case, hydrogen and oxygen, diatomic molecules, forming water. So, we actually indicate the reactants and products using chemical symbols, right? But that alone is not enough, right? Now, there is something called conservation of mass, which indicates that, yes, true, we are rearranging the atoms in a chemical reaction, but we don't create or destroy atoms. That is called mass of conservation, right? Conservation of mass, that is called conservation of mass.
Recording in progress.
Conservation of mass. The atoms or the substances don't get destroyed or they don't get created. So when we write a chemical equation, this is the equation that was previously shown to you. Hydrogen, oxygen, they together form water. But now if you look at that equation, there is one oxygen molecule here, but there are two molecules here as a reactant. So actually what happens is one oxygen atom gets destroyed here. Does it happen? No, right? So the reactants, the mass of the reactant should be equal to the mass of the products. So what actually happens is this. Two hydrogen molecules react with one oxygen molecule, forming two water molecules. Now, these two, number 2 or 3 or 1 or whatever it is, 1 of course we don't write. So those are called coefficients. We actually write the coefficients looking at the conservation of mass, the number of atoms of each side. So here, now I told you that here the number of oxygen does not match. So what can we do to make it equal? There is 2 here, 2 oxygen atoms. Here there is 1. So to balance it, we can put 2 in front of water. Right now what happens? There are 4 hydrogen molecules, hydrogen atoms here, but there is only 2 here. So we can put 2 as a coefficient. Now the number of atoms is equal. Reactants, products. So we are calling this balancing the equations. We have to balance the equations. When we write a chemical reaction, we have to balance the equation. Right? So that is what we are going to do now. At the exam, you will be asked to balance a simple equation, okay? Also, putting coefficients is done, and also the physical state is indicated. Physical state. Now, AgBr, this is silver bromide, solid. S stands for solid. L stands for liquid. AQ means aqueous. What is aqueous? What do you mean by aqueous?
Aqueous means a water solution. Sodium chloride aqueous means a salt solution. Sodium chloride dissolved in water. So that means that we actually show that using this symbol AQ. Right? If now silver bromide is solid, so we indicate it using S. So that is the correct way to show, give chemical equations. Now here, when we, so what happens when ammonia is formed? Nitrogen N2 reacts with hydrogen to form ammonia. The chemical formula is given here, the molecule. Now look at this. 2 nitrogens, 1 nitrogen. So how can we start to balance the equation? If we put a 2 in front of ammonia, then there will be 2 nitrogen atoms on the left-hand side and 2 nitrogen atoms on the right-hand side, right? But then when we, so we put 2 here, right? 2 here. Then when we look at the hydrogen, the amount of hydrogen. So nitrogen, now there is a 2 in front. So altogether 2 into 3, 6 hydrogens are here. Right? 2 into 3, 6 hydrogens are here. Now we put 2 here. 2 into 3, 6 hydrogens are there. So what can we do here to balance it? We can put 3 here. Now 2 nitrogens are there and 6 hydrogens are there on both sides. Okay. This is how we should be actually. Right, so these are some guidelines, hints to balance chemical equations. So here in an equation, when we write the chemical formula, we put subscripts, right? We put subscripts, SO2. This is a subscript. Okay, this is a subscript. Our superscripts ki udata tiyanewa, mewa subscripts. Right? These are subscripts. We don't touch the subscripts. Right? We don't do any change to the subscripts because they are part of the chemical equation, the chemical formula. Right? That gives the identity of the chemical formula. So we don't change anything. The only thing that we do is that we change the coefficients. That is the big numbers that come before chemical formula. We change the big numbers, right? So that is what we do. So if we take this equation, zinc sulfide plus oxygen, zinc oxide plus sulfur dioxide, right? So like people do it in different ways. Now here it says oxygen is even on the left hand side but not on the right hand side. මෙතන දෙකක් තියෙනවා කියන්නේ even number එකක්. Here this is 2 and 1 3. It's odd number.
ඒක නිසා අපි මේක දෙකෙන් වැඩි කරනවා. දෙකක් දානවා. right? ඊට පස්සේ මොකද කරන්නේ අපි? එතකොට මොකද්ද change වෙන්නේ? What changes? ගමන් sink එක වෙනස් වෙනවා නේ. The number of zinc atoms change. Here we have 2 zinc atoms on the right hand side, but here there is only 1 zinc atom. So we put 2 here. There is zinc uthari, other than zinc hari. Now, before balancing oxygen, we can have a look at sulfur. වෙනම තියෙන එකක් නම් අපිට බැලන්ස් කරගන්න ලේසියිනේ. දැන් මෙතන zinc sulfide තියෙද්දි sulfur අපි බලන්න ඕනේ. zinc විතරක් නෙවෙයි sulfur. So 2 sulfur atoms are here, but here there is only 1 sulfur atom. ඒක නිසා we put 2 here. Now zinc is okay, sulfur is okay. The only problem is oxygen. Here මෙතන 2 oxygens are here. මෙතන I4 තියෙනවා. And 6 oxygens. මෙතන 3 දාන්න ඕනේ. Now, even though I explained to you these balancing chemical equations, you have to do it to get the practice. Just listening to me and watching what I do will not be enough. So we will practice how to balance equations. So at home you can go through this slide, how they balanced silver. Okay, there is another thing that I should mention. So when there are ions, polyatomic ions, it can atom එකට වඩා තියෙන සමහර elements උත් එකට වඩා තියෙන ion එකක්. Now here it's nitrate. තියෙනවා නම් මේ sodium nitrate, NO3. You should take it as a whole, completely. Take it as a whole, right? The nitrate කියන එක ඔයගොල්ලන් nitrate විදිහටම තමයි balance කරන්න ඕනේ. Oxygen වෙනම nitrogen වෙනම නෙවෙයි. මෙතන මේ පැත්තේ nitrate තියෙනවා, මේ පැත්තේ nitrate තියෙනවා. එතකොට nitrate එක ඒ unit එක ඒ විදිහටම අරන් තමයි balance කරන්න ඕනේ. Right? So that is something that you have to do. දැන් මෙතන අපි ගමු. මෙතන ඉස්සෙල්ලාම iron and carbon අමතක කරනවා ඉස්සෙල්ලාම. Because they actually stand alone and we can put anything in front of these chemical species. මේ අපිට ඕන එකක් carbon ඉස්සරහට දාන්නත් පුළුවන්, iron ඉස්සරහට දාන්නත් පුළුවන්. ඒක නිසා as the first step we can actually neglect iron and carbon and try to balance the other molecules. In this case, then if we forget about iron and carbon, the one that is left is oxygen. Then මෙතන O2 molecule එකක් විදිහට නැහැ. Right? එනකොට අපි iron and carbon මෙතන තනියම ඉන්නවා. ඒක නිසා අපි මේ වෙලාවේ we look at oxygen. Then මෙතන oxygen is odd. 3 නේ. So we put 2 here. What is the number of oxygen atoms here? 2 into 3, 6. Now we go to the right hand side. If we put 3 here, then there will be 6 oxygen atoms. So oxygen is, okay, balanced. Then it's easy. Carbon, 3 carbons are on this side. Then we put 3 here. Then 4 iron atoms are here. Then we put 4 here. right? So, yeah. So what is stoichiometry? Then we've actually learned what is stoichiometry. We will just introduce the term here, stoichiometry. The study of the mathematical relationships between the substances in balanced chemical reactions. Allows for calculation of amounts of reactants or products in a chemical reaction. Here. To confirm, this should be LAW. To confirm the laws of conservation of mass, there must be same number of each type of atoms on both sides of the arrow, right? Here, the number of atoms should be equal to the number of atoms here of each element. Therefore, balancing of the equation is important, right? Hydrogen, oxygen, water. So we actually balanced this equation previously. So what information can we obtain? Right. Here, but the information that we can get here is that 2 molecules of hydrogen react with 1 molecule of oxygen to give 2 molecules of water. So that means 2 moles of hydrogen will react with 1 mole of oxygen to give 2 moles of water. So we can actually use this information for many things, including to find out the optimum amounts of different reactants to get the maximum yield. Here now, that is called stoichiometry. Now we take this equation, carbon monoxide plus water giving carbon dioxide. 2 moles of carbon monoxide react with 1 mole of oxygen to give 2 moles of carbon dioxide. The molar ratio of carbon monoxide to carbon dioxide is 2:2, that is 1:1. Right? Then ratio එක ගත්තොත් 2:2යි එහෙම නැත්නම් 1:1යි. Carbon dioxide එකකින් මේවා දෙකක් හැදෙනවා. දෙකකින් දෙකක් හැදෙනවා. Right? ඒ කියන්නේ එකක් ගත්තොත් එකක් හැදෙනවා. So that is called the stoichiometry between carbon monoxide and carbon dioxide. Right? So if 4.8 molecules of carbon monoxide react with oxygen, it will produce 4.8 moles of carbon dioxide, as the mole ratio is 1:1. Now we are going to learn the concept of limiting reagents. Now we know that certain amount of reactants react to give certain amount of products. So when we do carry out a reaction, is it wise to put
reactants without doing any calculations? Is it okay to put everything that is available as reactants? Obviously, no. We should calculate what amount reacts with which amount of the other substance, and we should let the reaction occur using those quantities. Or we can think of what is the amount of product that I want. To get that product, what are the quantities of the reactants that we should use? So now there is this term called limiting reagent. So we are going to learn about that now. When carrying out a reaction, the reactants are not usually present in exact stoichiometric amounts, right? Normally, they do not present in exact stoichiometric amounts because the goal of a reaction is to produce the maximum quantity of a useful compound from the starting materials. We should do proper calculations. Therefore, one of the reactants tend to be O. Now, because if we don't do the calculations correctly, of course, one reactant will be over before the others. So then, what is the limiting reagent? What is the limiting reactant? If one reactant gets over, like is used up faster, and if it is over now, while still there are other reactants, what is the limiting reactant? Reactant that is completely consumed before the others is called the limiting reactant or reagent. It is a reactant used up first in the reaction. So excess reagents or other reagents are called excess reagents. They are present in quantities greater than the amount necessary. Okay, the amount of product will always be determined by the quantity of limiting reactant. Now, when we take the product, okay, product එක ගත්තොත් ඒක හැදෙන්නේ limiting reagent එක තියෙනකන් විතරයි. Once it is used up, then one reactant is not there, then the reaction will not take place. Now let us look at an example. So this is a balanced equation. NO, 2NO in the gaseous state, gas state, oxygen, gas state, 2 NO2 molecules, gas state. So this reaction is a balanced reaction. So shall we have a look? Nitrogen, 2 nitrogen on this side, 2 nitrogens on this side. 4 oxygens on this side. 2 into 2 is 4. And 4 oxygens on this side. It's a balanced equation. The question is, if 8 moles of NO react with 7 moles of O2, what is the limiting reactant? 8 moles of NO, 7 moles of O2, what is the limiting reactant? කොහොමද බලන්නේ reactant එක අඩුවෙන් reaction එක වෙන එක තමයි reactant එක කියන්නේ නේද? Then if we look at the stoichiometry between NO and NO2, what is the stoichiometry? NO and NO2, look at this stoichiometry. This reactant and product. What is the stoichiometry? මේකේ මේ equation එකෙන් මොකද්ද ඔයගලන්ට කියන්න පුළුවන්? NO මවුල කීයක් react කරොත්ද NO2 මවුල කීයක් හැදෙන්නේ? හරි. එකට එකයි. right. එකට එකයි. හැදෙන්නේ. එතකොට if 8 moles of NO react with 7 moles of O2. දැන් මෙතන 8 තියෙනවා NO. එතකොට NO2 කීයක් හැදෙනවද? එතනත් 8යි නේද? දැන් මේක එකට එකයිනේ. NO 8ක් moles තියෙනවා නම් NO2ත් හැදෙනවා 8ක් moles. නේද? එතකොට දැන් මෙතන ඔක්සිජන් 7ක් moles. ඒතර ඔක්සිජන් 7ක් තියෙනවා කියලානේ කියන්නේ. ඒතර ඔක්සිජන් 7කින් කොච්චර NO2 ගන්න පුළුවන්ද අපිට? ඔක්සිජන් දැන් තියෙනවා 7 moles. එකකින් කොච්චරක් අපිට ගන්න පුළුවන්ද මේ NO2? මේවා 7ක් තිබ්බොත් කොච්චරක් හැදෙනවද? yes 14ක් හැදෙනවා right. NO වලින් 8යි ඔක්සිජන් වලින් 14යි. එතන මොකද්ද ලිමිටිං රියේජන්ට් එක? කොතනින්ද නතර වෙන්නේ? දැන් මෙයා බැලුවොත් හිතන්නකෝ ඔක්සිජන් 7ක් රියැක්ට් කරන්න තරම් NO නැහැනේ. 8යිනේ තියෙන්නේ. නේද? NO 8කින් ඇත්තටම රියැක්ට් වෙන්නේ කොච්චරද ඔක්සිජන්? අපි නිකන් ඒ පැත්තට යන්න ඕනේ නැහැ. නමුත් හිතුවොත් NO 8ක් රියැක්ට් වෙන්නේ ඔක්සිජන් කීයක් එක්කද? මේ විදිහට අපි බලමු කියන්න මම යන්නේ. දැන් මෙතන දැන් ඔයගොල්ලන් දැනට උත්තර දුන්න එකෙන් නම් NO වලින් හැදෙනවා 8කින් 8ක් ඔක්සිජන් 7කින් 14ක් හැදෙනවා. එතන මොකද්ද ලිමිටින් ගත්තොත් NO2 8 ඉවර වෙනකන් විතරයිනේ කරන්න පුළුවන්. ඊට පස්සේ මේව කොච්චර තිබ්බත් වැඩක් නෑ 8ක් හැදිලා අතර වෙනවා. මෙයා 14ක් හැදෙන්න ඔක්සිජන් තිබ්බ කියලා වැඩක් වෙන්නේ නැහැ. In that case, the limiting reagent is NO, right? right. 4 හරි. කිව්වද හරි. දැන් මෙතන NO 8ක් තියෙනවා නම් එයාට maximum react කරන්න පුළුවන් ඔක්සිජන් ගාන කොච්චරද? ඔයගොල්ලන්ගේ යාළුවෙක් දාලා තියෙනවා batchmate කෙනෙක් 4යි කියලා. ඒක ඇත්ත. මොකද stoichiometric reaction එක ගත්තොත් NO වලයි oxygen වලයි what is the stoichiometry? What is the stoichiometry? ඔව් දෙකට එකයි. හරි. එතකොට මේවා 8ක් තියෙනවා නම් මේවා රියැක්ට් කරන්න පුළුවන් 4කටනේ. මේවා 7ක් තියෙනවා නමුත් රියැක්ට් කරන්න පුළුවන් 4කට. excess තියෙනවා oxygen. එතකොට limiting reagent එක වෙන්නේ මෙයා NO. මොකද මෙයා ඉවර වුණාම රියැක්ෂන් එක නතර වෙනවා අනික් ඒවා excess තිබ්බත්. right? එතකොට limiting reagent එක NO. දැන් මෙතන simply කියලා තියෙනවා අඩුවෙන් product එක හැදෙන එක තමයි limiting reagent. Reactant that produces fewer moles of product is NO. අඩුවෙන් හැදෙන්නේ මෙයාගෙන්. මෙතන 8ක් තිබ්බොත් 8යි හැදෙන්නේ. මෙතන 7ක් තිබ්බොත් 14ක් හැදෙනවා. ඒ අඩුවෙන් හදන එක තමයි limiting reagent එක කියලා කියන්නේ. මේව ටික පොතේ තියෙනවා අපි ටිකක් කරත් මතකද? zinc කරා, sulfur කරා, helium කරා. Terms, what is Avogadro number, what is the molar mass, and we calculate, yes? Do you want to practice to calculate the molar masses? It's so to අපි calculate කරා. අනිකව calculate කරන්න ආසද? Water? මට මතක කියන්නම් හයිඩ්‍රජන් වල 1යි ඔක්සිජන් වල 16යි. ඒතර water වල කොච්චරද? Right, 18යි. එතකොට calcium chloride, calcium වල 40යි, chlorine වල 35.5යි. වගේ තමයි මතක. calcium වල 40යි, chlorine වල 35.5යි. හරි, 111යි. එතකොට sodium hydroxide, sodium වල 23යි, oxygen වල 16යි, hydrogen වල 1යි. 23යි, 16යි, 1යි. right. ඊට පස්සේ මෙතන hydrogen chloride, hydrogen 1යි, chlorine 35.5යි. එතන මේක nitrogen 14යි. විසියටයි. මේක මතක විදිහට සල්ෆර් 32යි, ඔක්සිජන් 16යි. Okay, methane, carbon 12යි, hydrogen 1යි. right. මම හිතනවා දැන් ඔයගලන්ට පුළුවන් කරන්න මේ ටික නම් මට මතක නැහැ. මෙතන මැග්නීසියම් 3ෙන් වැඩි කරන්න ඕනේ. PO4 එකතු කරලා සම්පූර්ණ එක දෙකකින් වැඩි කරන්න. PO4 එකතු කරලා ඉස්සෙල්ලා සම්පූර්ණ එක දෙකකින් වැඩි කරන්න. right? එහෙම තමයි කරන්නේ. ඔයගලන් මේක හොඳට කරයි කියලා හිතෙනවා. Now let's try to balance equations. try කරමු. දෙකක් තුනක් හරි කරන්න. පළවෙනි දෙක කරමුකෝ. මේක C2H6 should be a subscript. මෙතන subscript එකක් මේක.
පළවෙනි එක බැලන්ස් කරලා කියන්න මට මොකක්ද කියලා. අමාරු ඒවා නම් ඔයගලන්ට දෙන්නේ නැහැ. නමුත් you should have the practice. Ammonia plus 2 oxygen, carbon dioxide plus 2 water molecules. Yeah, that is correct. Right, this is correct. 2 in front of oxygen. Two, 2. How about the second one? How about the second one? What is the answer? I think it's better if we try not to do that. It's kind of a bit complicated. The answer anyway is this. Um, 6. I think the answer is this.
Yes, this is 7. That's true. This is 7. 6, 8, 14. So this should be 7. So that is correct. And we can actually, this is the usual way of writing the balance equation. We don't put like with decimal places, but the second answer is also correct. EPM 293, your answer is also correct. You divided everything by 2. Okay. Then Shehari's answer is correct. Right. So shall we try to balance E? This is fairly straightforward, E. E. You should take the anion as a whole. Here silver nitrate NO3 minus. You should take it as a whole. What is the answer? E. So it's straightforward, right? Yes, the answer is correct. 2 here and 2 here, right? Because there are 2 nitrates here, so we put 2 in front of silver nitrate. 2 silver atoms, we put 2 here, right? Then yeah, I think that's it. I think you can handle this. Right. You've given the correct answers. Yeah. So now we know how to balance equations, right? So let's look at this example. So here, what is given below? If 856 grams of glucose. This is glucose. C6H12O6 is consumed by a person over a period of time. What is the mass of carbon dioxide produced? So what is the first thing that you should do here? What is the first thing that you should do? A chemical equation is given. Glucose, here it's glucose, reacts with oxygen. That is breathing, right? Glucose reacts with oxygen to form carbon dioxide and water. So we exhale carbon dioxide, don't we? This is breathing actually. So this value, the gram value, 186 grams of glucose, if we consume that much, what is the mass of carbon dioxide that is produced? So that is the question. What do we do first? මොකද අපි ඉස්සෙල්ලාම කරන්න ඕනේ මේකට? ඉස්සෙල්ලාම මේක බැලන්ස් කරගන්න ඕනේ නේද අපි? නේද? අපි ඉස්සෙල්ලාම මේක බැලන්ස් කරගන්න ඕනේ. ඉක්වේෂන් එක. හරිද? එතකොට බැලන්ස් කරපුවම අපිට එන්නේ බැලන්ස් කරපුවම එන්නේ 6යි 6යි 6යි. I hope you have a pen and a pen, something to write on. Yes, 6 in front of everything. I mean, apart from glucose, 6. High, high. Right? Okay. Then what should we do? Now the question is, if 186 grams of glucose is consumed, what is the mass of carbon dioxide produced? What is the then we have the balanced equation. What do we do next? අහලා තියෙන ප්‍රශ්නේ විදිහට අහලා තියෙන ප්‍රශ්නේ විදිහට මොකද කරන්න ඕනේ? දැන් මේක ඉස්සෙල්ලාම අපි මොකද්ද ස්ටොයිකියෝමෙට්‍රික් රේෂියෝ එක බලන එක නේද කරන්න ඕනේ අපි ඊට පස්සේ. ප්‍රශ්නෙට උත්තර දෙන්න නම්. නේද? ඊට පස්සේ මොකද කරන්න ඕනේ? RAM අපිට දීලා තියෙන්නේ. අපි ඒක හරව ගන්න ඕනේ එකක් ස්ටොයිකියෝමෙට්‍රික් රේෂියෝ එක ගත්තොත් ග්ලූකෝස් එකට කාබන් ඩයොක්සයිඩ් මොලිකියුල්ස් 6ක් හදනවා. එකට 6. ඒක ස්ටොයිකියෝමෙට්‍රික් රේෂියෝ. නේද? එකට 6ක් දෙන්නේ. එකට 6ක් තියෙනවා ස්ටොයිකියෝමෙට්‍රික් රේෂියෝ. ඊට පස්සේ අපි ගන්න දැන් අපි එක මවුල වලින් අපිට කතා කරන්න වෙන්නේ. එතකොට අපි මේ 186 ග්‍රෑම්ස් වල ග්ලූකෝස් 186 ග්‍රෑම්ස් වල තියෙන මවුල ප්‍රමාණය හොයාගන්න ඕනේ. ඒක කරන්නේ කොහොමද අපි? ඒක කරන්නේ කොහොමද? මේ ইনফরমේෂන් දීලා තියෙනවා අපිට. මේ ইনফরমේෂන් දීලා තියෙනවා. මොකද්ද කරන්නේ අපි? මේකේ මෝල මෑස් එක හොයාගන්න ඕනේ නේද අපි? මෙයාගේ මෝල මෑස් එක හොයාගන්න ඕනේ. දැන් කියන්න බලන්න මෝල මෑස් එක මොකද්ද කියලා? මෝල මෑස් එක මොකද්ද? 180. Hari. The molar mass is 180. You can calculate it. හරිද? ඊට පස්සේ number of moles එතකොට කොහොමද හොයන්නේ?
.75
4.75. හරිද? මං කිව්වා අටසිය 86 බෙදන්න ඕනේ නේද 180ෙන්? number of moles හොයන්න. මතකද අපි ඉස්සෙල්ලා කතා කරා number of moles කොහොමද ගන්නෙ අපි? weight එක නැත්තම් mass එක මේ බෙදනවා molecular weight එකේ. molar mass එකේ. අපි mm කියලා දාමු molar mass. ඒ molar mass එක 180යි. weight එක නැත්තම් mass එක 856යි. එතකොට number of moles කොච්චරද? number of moles කොච්චරද? ඉක්මනට කියන්න calculate කරලා. හරි. 4.755 අපි 76 කියලා ගමුද? ලේසි වෙන්නේ. 4.76 ගමු ලේසි වෙන්නේ. 45 ගත්තත් කමක් නැහැ. මෙතන 5 වලට වඩා ලොකු ඒවා තියෙන නිසා මම 76 කියලා අපි හිතමුකෝ අපි. 4.76 75 වුණත් කමක් නැහැ. then stoichiometric අපි ගත්තේ මොකද්ද? 4.7 අපි හිතමු 6 කියලා. 6 moles තියෙනවා of මෙතන තියෙන of glucose නේද? then අපි ඉස්සෙල්ලා බැලුවා glucose වලයි carbon dioxide වලයි stoichiometry. මේවා එකක් carbon dioxide කීයක් එක රියැක්ට් කරනවද? කීයක් එක රියැක්ට් කරනවද? You have to talk, otherwise how can we move forward? කොච්චරක් එක රියැක්ට් කරනවද? 6ක් එක රියැක්ට් කරනවා. එතකොට what is the amount of number of moles of carbon dioxide that will form? එකකට 6ක් නම් 4.76කට කොච්චරක් රියැක්ට් කරනවද? මේ හැදෙනවද? මොකද්ද කරන්න ඕනේ?
28.56.
හරි 28.56. ඒ කියන්නේ එකකට හැදෙන්නේ 6ක් නම් 4.76 6න් වැඩි කරන්න වෙනවා. එතකොට එනවා 20 කීයද 28.56 නේද?
56.
56 එනවා. ඊට පස්සේ දැන් මොකද කරන්න කියන්නේ what is the mass? අපි මවුල ප්‍රමාණය දන්නවා. අපි ඒක ඉස්සෙල්ලා ලියාගමු. 28.56 නේ. 6 moles. එතකොට මෙයා අහන්නේ උනට මෑස් එක. දැන් එතකොට මොකද කරන්නේ? අපි දන්නවා number of moles of carbon dioxide දන්නවා අපි. number of moles දැන් අපිට mass එක කියන්න කියලා කියන්නේ.
Equal.
not equal. equal කියන්නේ මොකක්ද mean කරේ? මම මෙතන stoichiometric coefficients ටික ඉස්සෙල්ලා delete කරා. number of moles දන්නවා of carbon dioxide. දැන් මොකද්ද mass එක? කොහොමද හොයන්නේ? කොහොමද mass එක හොයන්නේ? Hari, the answer is correct. The answer is correct. කොහොමද ඒක එතන ආවේ කියන පාත් එක කියන්නකෝ. මොකටද දෙන්න ඕනේ you will know how to do it. දැන් අපි මොකද කරන්න ඕනේ? අපි දන්නවා number of moles. We know the number of moles. Hari. මොකද කරන්න ඕනේ? We should take the molecular weight of carbon, molar mass of carbon dioxide. What is the molar mass of carbon dioxide?
44.
44. Right? දැන් මොකද කරන්නේ අර අපේ equation එක. Number of moles කොහොමද ගන්නෙ? weight එක එහෙම නැත්නම් mass එක බෙදනවා molar mass එකෙන්. දැන් අපිට මේක තියෙනවා molar mass එක තියෙනවා. කොහොමද weight එක හොයන්නේ? moles ගන්න මේක ඒක වැඩි කරනවා molar mass එක කියන්නේ 44. මේක 44න් වැඩි කරාට පස්සේ තමා අපිට මේකේ උත්තරේ හම්බ වෙන්නේ. What is the mass of carbon dioxide produced? යාළුවෝත් කියලා තිබ්බ විදිහට that is 1256.64. Right, so that is the answer. So think logically, practice this several times over and over again. Then you will understand how this problem can be solved. Okay, I will give you 10 minutes. Try to solve this problem. Before that, write down these values. Write down these values. Nitrogen 14. Nitrogen 14. Hydrogen 1. Carbon 12. Oxygen 16. Okay, so I'll give you 10 minutes. Now it's 2:38. So I'll give you time until 2:48. Right, solve this problem. Then we can discuss. I think you have to, on the practical day, you have to do practicals. One related to the UV visible spectrophotometer, paper chromatography, and something else, titration. I'm not sure whether you'll be able to practice this question, but you have the book with you, the course module, so you can practice the questions. So here, according to the balance equation, 2 moles of ammonia react with 1 mole of carbon dioxide to form 1 mole of urea. Then the weights of ammonia and carbon dioxide are given. So using the molar mass, the number of moles can be calculated. Right? So according to the stoichiometric ratio, 2 moles of ammonia produce 1 mole of urea. So if we take that information, 37.12 moles of ammonia will produce 18.55 moles of urea. Right? Then if we take carbon dioxide, the number of moles of carbon dioxide is 25.95 moles. Then it can, since the stoichiometric ratio is 1:1, it can produce 25.95 moles of urea. Now, the reactant that leads to a smaller amount of urea is ammonia, and because of that, the limiting reagent is ammonia. Right? It's ammonia. Now then, the mass of urea formed. So we know this limiting reactant is ammonia because it leads to the formation of a smaller amount of urea. So we have to think now that all the ammonia molecules react, right? Because of that, what is the amount of urea that is formed? So the ratio was 2:1. 2:1. Is it 2:1? Is it 2:1? It's 2:1, right? Right. Calculate the mass of urea formed. Right. Is this correct? Did you try to solve the problem?
Madam, moles of NH3, the 632.2 divided by 17 is 37.18.
18. Okay, 37.18. Then it has to be divided by 2, isn't it?
Yes.
Does it come to 18.55?
18.59.
Okay. Now there are small mistakes. But yeah, there are small mistakes. We have to correct those small things. So the thing is that it has to be divided by 2 because the stoichiometry between ammonia and urea has to be considered. since the number of moles of ammonia was 37.19, you said?
8, madam. 1
18.
That is, oh, yes.
Yeah, 37.18. Now we have to divide it by 2 because the stoichiometry is 2:1, right? We have to divide it by 2. So we have to, what is the molar mass of urea?
60, madam.
60. So we get the number of the weight, the mass of urea. I think this also has to be changed a little bit, isn't
Yes,
it?
ma'am. Yes, madam. 1115.4.
15.4. 15.4. Right. Then excess reagent is carbon dioxide, right? The ratio of ammonia to carbon dioxide is 2:1. So 37.18, right? 18 moles will react with 2:1. 18.59. 59 moles of carbon dioxide, right? This 2:1. So we have to divide this by 2. Then excess moles of carbon dioxide are what? This is the amount that is already there, right? 25.95. Is this correct?
Yes, madam. That's correct.
25.95. So we have to subtract the amount that will react with ammonia. So we get 7 point what?
36.
36 moles, right?
Right.
Number of moles will be this much, right? So if we want to get the weight, we have to multiply the number of moles by the molar mass. The molar mass of carbon dioxide is 44. So we get the answer
323.84.
84, right? So that is the answer. I hope that I'm sure that most of you have got these answers, but you have to practice. Just don't keep the answers with you. Even now, we will share the slides with you. So don't look at the answer, but practice. Then it will be easier for you at the exam because you will actually know what to be done. So we've finished talking about the mass relationships. The next step, the next chapter is
Recording stopped.
the next chapter is okay, one moment. About introduction to food chemistry. Yes, we will move to the next topic, food chemistry overview. So, food is more than cooking. In cooking, you might follow a recipe, but in food science, we try to find out the science behind cooking, right? So why we do this? What is the effect of this on a property? Likewise, we are talking about science actually in food chemistry. So you can see different types of pictures here. So baking, cookies, strawberry jam, and minimally processed foods. So these are things that we actually encounter very frequently. So it's interesting to know what are the things that happen during these processes. So what is a food? Any substance that can be eaten, and usually they have carbohydrates, proteins, lipids, water, and sometimes micronutrients and things like that. The major food components are carbohydrates, proteins, lipids, and water. And minor chemical constituents are vitamins, minerals, pigments, flavors, enzymes, and antioxidants. Vitamins, minerals, we know they are essential. Then pigments, color-giving compounds, flavors such as vanilla flavor, chocolate flavor. Enzymes are involved in, we actually use enzymes in the preparation of foods. And there are many other substances such as antioxidants, anti-cancer substances with anti-cancer properties, antimicrobial properties, etc. And these constituents determine the flavor, color, structure, and taste and nutritive value of food. So these constituents, it's very important that we learn about these constituents, especially the main constituents, carbohydrates, proteins, lipids, and water, because they determine the flavor, color, structure, and taste and nutritive value. So if I take a simple example, how water is important. So there is rice, cooked rice. We can eat cooked rice. But if the rice is dehydrated, if we keep cooked rice, so excess rice is kept exposed to the sun to get rid of excess water so that we can prepare agala later, right? So when there is no water in the grains, can we eat it? No. So water plays a major role in actually, so without water we can't eat. So importance of food, there are many reasons why we should take food. Obviously, we can't live without food, right? So foods are usually rich in either carbohydrates, proteins, and fats. It is important that we eat food because we get energy through food. 1 gram of carbohydrate or 1 gram of protein will give 4 calories, while 1 gram of fat gives 9 calories. So carbohydrates or foods that give us energy involve sugars, cereals, pulses, oilseeds, roots, and tubers. Then bodybuilding. So these bodybuilding, like us and also the professional bodybuilders, they take foods rich in proteins. Proteins can be divided into two groups. One group is protein from animal sources. They contain all the essential amino acids. So what are the essential amino acids? So do you know what amino acids are? Okay, I'll explain this point after we study what essential amino acids are, right? So protein-rich foods come under two categories. I will explain this point to you when we learn about essential and non-essential amino acids. Then protection and regulation. For protection and regulation, we need to get proteins, vitamins, and minerals. The functions include maintain heartbeat, temperature regulation, blood clotting, etc. So to get proteins, vitamins, and minerals, we can take many different foods, including green leafy vegetables, fruits, fish, meat, etc. As I mentioned previously, for the maintenance of health, phytochemicals, including antioxidants, can be taken. What are phytochemicals? Phyto is plant, chemicals means chemicals, right? So chemicals in the plants can be antioxidants. We know that antioxidants are very important. It's important that we take antioxidants through our diet. Can you give me some examples of antioxidants?
Ginger,
Ginger,
turmeric,
turmeric. In turmeric, there are antioxidants called curcumin. In ginger also, there are antioxidants. In both ginger and turmeric, there are antimicrobial compounds and anti-cancer compounds as well. Right? So those are phytochemicals. And there are many other compounds with many other properties, such as anti-diabetic properties. Can you name certain things that we take in because those have anti-diabetic properties? Anti-diabetic කියලා අපි මොනවද ගන්නෙ? හොඳයි කියලා.
low sugar content,
I'm sorry?
low sugar content food,
Yes, low sugar. Yeah, food with the low sugar content, that is true. But specifically, because those, so when we eat or drink those foods, we think that the blood glucose level will go down. Such foods, Belibal, Pranavara, Tebu, red rice කියන්නේ මෙහිමයි. අර අඩු කරන්නේ නැහැ. තියෙන මේ blood glucose level එක අඩු කරන්නේ නැහැ red rice කෑවා කියලා. 180ට තියෙනවා නම් එයා කෑවා කියලා එක 160ට නැහැ. නමුත් it's better than eating white rice. මොකද absorption එකයි release of glucose into the bloodstream becomes low. Yes, Kovaka. Right. So those are the things. So for the maintenance of health, it's important that we take food, especially fruits and vegetables. Bitter gourd, karavilla, wild coriander. Wild coriander කියන්නේ වල් කොත්තමල්ලි. Yes. Bitter gourd, karavilla. Yes, those are things that we take. Leafy vegetables. Yes, because we think that leafy vegetables have vitamins, minerals, and fiber gives fiber. Those vegetables give fiber. Right.
Recording in progress.
Now, first we will look at water. I told you water is very important. So we will be studying about the chemical and physical properties of water, water activity, and food stability. It's the most common liquid and the most widely distributed pure solid ice. It is the most common liquid and solid, pure solid, which is ice. It's essential to life. It plays main roles in regulating body temperature as solvents, as a lubricant, as a carrier of nutrients and waste, as a reaction medium, etc. So it is very important that we drink sufficient water every day. We require about 2 liters or 8 cups of fluids every day. Importance of water in food science. Water. So the water content is very important, isn't it? Now look at this fish. This is fresh fish. If we remove the water in the fish, what will it become? You can make karavella, dry fish. Neither. These grapes, if we, there's a special kind of grapes, if we do dehydrate, we can get raisins. Right? So what is very important? And so let's take a look at the water content in different foods. Meat, the water content is between 50 to 80%, fruit 80 to 95%, and vegetable 75 to 95%. The water amount, form, location largely influence the structure, texture, appearance, and taste of foods. Now it's very important. So let's take an example. Okay, say a cookie. We like to eat cookies when it's crunchy, but if water is absorbed, there will be no microbes there. But if the cookie absorbs water, then do we like to eat it anymore? No. The taste, appearance, texture, everything is affected by the water amount that is there. So we actually talked about the water molecule previously as well. It has 2 hydrogen atoms covalently bonded to a single oxygen atom. Right? Something like this. Oxygen, 1 atom is shared, like 2 atoms, one from oxygen and one from hydrogen. Right? This is a covalent bond, lone pair, lone pair. Right? So it has the bond angle is 104.5, and it has approximate tetrahedral structure. You don't have to worry much about it, but it has a tetrahedral structure. yeah, tetrahedral. Now, can you see the structure? This is the electron pairs point towards the corners of a tetrahedron. That is why we call it tetrahedral. So water molecules, each water molecule is bonded to 4 other water molecules. And it has a 3-dimensional structure. Right? Now, if you take the molecule at the center, right, it is bonded to 4 other water molecules through hydrogen bonds. We learned about hydrogen bonds today, right? Through these intermolecular forces, one molecule is bonded to 4 other molecules. Each of these molecules are bonded to 4 other water molecules likewise, right? So I told you that boiling point is very high in water. It's 100. That is because of this, the strength of the intermolecular bonds and the 3D structure they form. For a molecule to go from the liquid state to the vapor phase, these 4 bonds should be broken. It's very difficult because these are hydrogen bonds. And because of that, the boiling point of water is very high. Therefore, extra energy is needed to break intermolecular hydrogen bonds. This explains the unusually high values for melting and boiling points. So this is just for you to get an idea. Now this oxygen, carbon, nitrogen, fluorine are on the same period, right? So these are their hydrides: water, ammonia, methane and hydrogen fluoride. Okay. මේ elements oxygen, carbon, nitrogen, fluorine තියෙන එකම period එකේ second එකේ මේ හැම එකම hydrogen එක හදන molecules තමයි මේ දීලා තියෙන්නේ. Now when we take this boiling point, the boiling point of water is 100, whereas the boiling points of other molecules are pretty low. නේද? දැන් මෙතන ගත්තත් melting point එක 0, අනික ඒවා ඊට වඩා ගොඩක් අඩුයි. Right? So the high melting and boiling points of water are because of the strong intermolecular bonds among water molecules. Therefore, extra energy is, yes. And the other interesting thing is the density. Density of water is approximately 1 grams per cubic centimeter. Density of ice is low. That means when water freezes, it expands. Right? So if you fill water in a plastic bottle, close it tight, and if you keep it in the refrigerator, most probably the bottle will crack if it's a plastic bottle. Right? So because ice is less dense than water, that means when water freezes, it expands. Depending on the type of interaction with water, the substances can be categorized into 2 groups. Some substances are hydrophilic, the other ones are hydrophobic. Hydrophilic substances are water-loving substances. Hydrophilic, philic means loving substances. They are polar molecules. So, for example, if we take sugar, salt, and things like that, they like water. They are water-loving substances. And there are hydrophobic substances, which are water-fearing substances. They are non-polar molecules. So we talked about polarity. If the molecules are polar, they are dissolved in water. But if they are non-polar, they do not dissolve in water. An example is oil. If we put some oil into water, the two layers will separate and oil will be on top of above the water layer. So if we want to mix the two layers, we have to put emulsifiers. We have to put emulsifiers. Emulsifiers, of course, have one part dissolved in oil and one part dissolved in water. Then emulsifier එකක් ගත්තාම ඒ molecule එකේ කොටසක් water loving, කොටසක් oil loving or lipid loving. ඒතරේ දෙකේම දිය වෙනවා. එක part එකක් water වල දිය වෙනවා අනිත් part එක oil. ඉතින් එහෙම properties තියෙද්දි we can actually try to mix oil with water, forming an emulsion. Yes, can we have a 10-minute break and start? It's 10-minute break. Now it's 3:24. Let's meet at 3:35. Okay. So we talked about water being a solvent. Water loving compounds, hydrophilic compounds dissolving water, whereas hydrophobic substances form a separate layer. But if we use emulsifiers, then we can actually disperse water and lipids. Now we are going to talk about water activity. What is the term water activity? There are two terms, water activity and water content. So the word water content is familiar to us, but the problem is water activity is not the same as water content. There is a relationship. So water activity, so how can we explain water activity? So now in foods, we have two kinds of water, bound water and free water. Bound water is strongly bound to specific sites in the food. They are strongly bound to food, and because of that, the bound water is not available for microbial growth or chemical reactions. It actually, bound water functions as part of the solid food, right? But the free water is an indication of water activity. Free water is an indicator, right? So water content alone is not reliable indicator of perishability. Water content, I told you now, if we take water content, it involves both the bound water and free water. But free water is the type of water that is available for microbial reactions and chemical reactions, microbial growth and chemical reactions. So it is water activity that we should use when we try to predict the perishability and things like that. The term water activity was developed to describe the intensity with which water is bound, associates with other compounds. It gives an idea about water availability for hydraulic, chemical, and microbial reactions. Water availability. So water activity gives an indication of water availability. Food stability, safety, and other properties can be predicted more reliably from water activity than from water content. So shall we define what water activity is? Right, so don't worry much about it. Water activity is equal to the vapor pressure of water in a material, rho, to the vapor pressure of pure water at the same temperature. So if you are asked to define water activity at the exam, write this equation, AW, water activity is equal to rho over rho naught, and give rho over rho naught is relative vapor pressure. Right? So in simple words, vapor pressure is highest when it comes to pure water. In any food, the water vapor pressure will be lower than that of pure water. Right? So because of that, water activity will lie between, it says 0.1 to 1. Actually, it should be less than 1, water activity. Because rho is always lower, smaller than rho naught. Rho is smaller than rho naught. Rho naught is the vapor pressure of pure water. If the water activity is high, rho is high, but not as high as rho naught. Right? So you define rho over rho naught as relative vapor pressure. Yes, water activity scale extends from 0 to 1, pure water. That's 0 to 1, not 0.1, 0 to 1. Water activity is usually measured as equilibrium relative humidity, ERH. So we get ERH by multiplying water activity by 100. If the water activity is 0.7, then ERH is 70%. Very simple. Water activity multiply by 100, then you get ERH. Water activity multiply by 100 and you get ERH. This is a chart that shows the water activity of different types of foods. As you can see, fresh meat, fish has a very high water activity. But if you take biscuits, 0.3, milk powder, 0.2, instant coffee, 0.2. Likewise, when the water activity, so when the food becomes dry, the water activity becomes lower and lower. So how can we lower the water activity? How can we control water activity? To lower water activity, we can remove water. How can we do that? We can actually do dehydration or drying. So we actually dry pieces of turmeric in the sun, and then I told you about cooked rice. We dry and then we do solar drying, right? And then or sun drying. So what else? Cooked rice, turmeric pieces. What else do we dry? Solar dry.
Grain,
I'm sorry?
grain, daan,
Grains. Yes, grains.
dehydrate, man.
Yes, dehydrate using sun drying, I said, but we do a dehydration of other like food items as well. We have what? Dehydrated jackfruit. We have dehydrated jackfruit, don't we? We can cook jackfruit at home. We can have you seen dehydrated jackfruit?
Yes, ma'am.
Yes. And we have dehydrated brinjals, dehydrated bitter gourd, vegetable, right? So in instant soups and even in like Maggi noodles, instant noodles, we have a sachet with dehydrated vegetables and other things. So yeah, we dehydrate many things to reduce the water activity so that we can keep the food for a longer period of time. And we can add solutes as well. When we, can you give me an example? Add solutes. How about
Lime, salt,
salt, right? We can prepare dry fish. Karaval hadaddi. We add salt. Because salt, as I mentioned previously, water gets bonded to salt, and because of that, the water activity decreases. Also, we add sugar. In the preparation of jam, we add sugar. So we reduce the water activity.
honey,
මොකට දාන්නේ?
meat,
Meat, හරි. Meat වලට දානවා, honey. Right. What else? Lowering the temperature. So when we freeze, මොකද කරන්නේ? We are converting liquid water to solid water so that water will not be available for any reaction. Right? So we can lower the temperature and control water activity, or we can combine. We can combine. Right? So we can combine. Yeah. And also, right. Water, food stability and water activity are closely related. We actually learned that in like instead of water content, if we use water activity, that is more reliable, especially when we talk about food stability. Whatever activity influence food stability by affecting chemical reactions and microbial growth, so that we can use water activity to predict food spoilage and useful in food design. Right, now let's talk about carbohydrates. So you have a fair idea now about water. Why is it important? The molecule, why is it important? The things that are dissolved in water and how we can, what is the difference between water content and water activity? Why is our water activity more reliable, and how can we control the water activity? So you know about those things. And now we go to have a look at carbohydrates. So we are going to basically talk about carbohydrates in food, structure and nomenclature and functions of carbohydrates. Carbohydrates in foods, any food that is particularly rich in starch, sugar and fiber. So those are foods rich in carbohydrates. Then common food sources of carbohydrates are grains, legumes, fruits and vegetables, sugarcane, sugar beets, root and tuber crops, and also milk. There is lactose. So these are common food sources of carbohydrates. Carbohydrates occur in plant and animal tissues, and in microbes in many different forms and levels. Comprise greater than 90% of the dry matter of plants. If we take plants, more than 90% of the dry matter is carbohydrates. There is water, a lot of water. If we disregard the water content, the rest, if we take the rest, 90% is carbohydrates. They're abundant, widely available, and inexpensive. And because of that, we actually like very much to incorporate carbohydrates in food.
So the main energy sources of humans are starch, lactose, sucrose, glucose, and fructose. These are the main energy sources of humans. And the general elemental composition is this. Carbohydrates have carbons, hydrogens, and oxygens. And the elemental composition is CxH2OY. Right? So if XY can differ. X and Y. Composition is this. So if we look at the different groups of carbohydrates, there are monosaccharides, disaccharides, oligosaccharides, and polysaccharides. A saccharide is sugar. If there is only one sugar in the compound, we call it monosaccharide. If there are two sugars, we call those things disaccharides. If there are 3 to 10 saccharides, they are called oligosaccharides. And if there are more than 10 sugars, we call those things polysaccharides. So simple carbohydrates are sugars. They are monosaccharides and disaccharides. And complex carbohydrates are polysaccharides, which are starches and fibers. The names of monosaccharides, that means single sugars, and disaccharides are very often, they end with the suffix "ose." Glucose, sucrose, the end is "ose." Sucrose, lactose, OSC, ose. Ending is like that, the suffix "ose." If we take monosaccharides and disaccharides. So monosaccharides has one sugar unit. They're the simplest carbohydrates. Cannot be broken down to simpler carbohydrate molecules by hydrolysis. Cannot be broken down to simpler carbohydrate molecules. They are usually colorless and water soluble. Simplest carbohydrates cannot be broken into simpler carbohydrate molecules, usually colorless and water soluble, such as sugar that we have, sucrose. Monosaccharides examples are glucose, galactose, fructose, and ribose. Actually, now these are single sugar units. They join together to form disaccharides, oligosaccharides, and polysaccharides. These sugars have a carbonyl group, that is CO group, CO, right? If the CO group is an aldose, CHO, this group is known as the aldose. COH, right? This group is known as an aldose. So just CO is known as a ketose. Depending on the carbonyl group, we call these molecules aldoses and these molecules ketoses, right? Aldoses and ketoses. So these monosaccharides can have a number of carbon atoms, and if the functional group is an aldehyde, it ends with -ose. If the functional group is a ketone, it ends with -ulose. Tri, 3 is tri. This is triose, this is triulose. 4, tetra, tetrose, tetriulose. 5, penta, pentose, pentiulose. 6, hexa, hexose, hexulose. 7, hepta, heptose, heptulose. Heptose, and octa, 8, octose, octulose likewise. Then we can combine two, like in the due to the combination of two monosaccharides, we get disaccharides. Here, two glucose molecules bind together to form maltose. The bond between two monosaccharide molecules is called a glycosidic bond. Right? Then මේ glucose molecules දෙකක් එකතු වෙලා disaccharide එක හදනවා. මේ වෙලාවේ maltose. එච්චර මතක තියාගන්න ඕනේ නැහැ. Molecules දෙකක්, monosaccharides දෙකක් එකතු වෙලා disaccharide එකක් හදනවා. The bond that is formed between the two molecules is called a glycosidic bond. Right? So this is important. You should know the name of the bond, glycosidic bond. මෙතන C1 and C4 වල තියෙන තැන a new bond is formed. In the case of maltose, right? Glucose, maltose, a bond is formed that is a glycosidic bond. Forget about what is in the front. 1,4-alpha. Just forget about it and just remember that there is a glycosidic bond between the two monosaccharides. Then we will talk about sucrose. Sucrose is the most abundant disaccharide and the main form in which carbohydrates are transported in plants. When it comes to plants, carbohydrates are transported in the form of sucrose, but in our bodies, carbohydrates are transported in the form of glucose. But in the plants, we get sucrose. And also sucrose is used for fermentation, bakery products, confectionaries, that is like fermentation, like in bakery products and in wine and like other types of alcoholic preparation of alcoholic beverages, things like that. For confectionaries, we use sucrose. So oligosaccharides contain 3 to 10 sugar units joined by glycosidic bonds. Right? Only a few oligosaccharides occur in nature, and mostly, so suppose there are polysaccharides, they have more than 10 sugar units. So we can break down the polysaccharides and get oligosaccharides. So some of the oligosaccharides are fructooligosaccharides, raffinose, and stachyose. Now here, so polysaccharides contain greater than 10 sugar units. Examples include starch, glycogen, cellulose, chitin, and hemicellulose. The starch is the form of storage of carbohydrates in plants, starch. In us, in animals, carbohydrates are stored as glycogen. So starch consists of a large number of glucose units joined together by glycosidic bonds. Sources of starch include grain seeds, tubers, and fruits and vegetables, sources of starch. right? Grain seeds, of course, rice, even chickpea and things like that. Tubers, fruits, vegetables have starch. Food uses are adhesive, bind, gelling, moisture retaining, stabilizing, texturing. For many things and thickening, we use starch. So cornstarch is used to thicken what? We use cornstarch to thicken what? What are the things? අර සුප් එහෙම අපි cornstarch දානවා නේද thicken කරන්න. ඒ වගේ දේවල් වලට we use starch. And bakery industry, starch is used. Now here in the bakery industry, can you, I think we all have noticed that there is a brown color. We get a brown color on the surface. That is because of sometimes caramelization and Maillard reactions. Caramelization, so caramelization is a reaction that takes place between sugar molecules and they produce nice aromas and a brown color, right? So that is due to sugar molecules. So in bakery industry, we see caramelization as well as Maillard. In Maillard reactions, amino acids interact with sugars, right? So in the case of confectionery, like this caramel pudding, we know very clearly we use sucrose and we caramelize sucrose and we get the nice flavor and this the caramel. That is, we use carbohydrates to get these nice flavors and colors. So functions of sugar. One is for caramelization and Maillard reactions, right? Caramelization and Maillard reactions. The other functions include to provide energy, sweetening agent, to improve palatability of nutritious foods. That means eating ability, eating likeness to develop, to improve stability of canned foods as a preservative. Stability of, now if we take canned foods such as pineapple chunks and things like that, we have to put sugar to maintain stability. Sometimes we use like juice, pineapple juice, so which contains sugar. As a preservative also we add sugar. One example is jam. It's a main ingredient of jam. Also it acts as a preservative, sugar. So now there is this traffic light system, red, yellow, green. Red, yellow, green. So red is when the sugar content is very high, greater than 11 per 100 milliliter. If it is between 2 to 11 grams, yellow code has to be given. Less than 2 grams, we can give the green color. But the problem is I'm not sure whether it's impossible. It's very extremely difficult to go to the green zone without incorporating a sweetener, artificial sweetener. And we don't know how good is to take in artificial sweeteners. I told you about Maillard reactions. It's a form of non-enzymatic browning. Amino acid and reducing sugars react to give these brown color polymers and nice aromas. So it happens in grilling. Nice flavors and aromas are developed. Sugar and amino acids. Here, roasted bread, biscuits, French fries, malted barley, fried onions, dried or condensed milk, roasted coffee, burnished surface of buns, crust, and bread and cake. So Maillard reactions take place. Even when we make milk toffee, caramelization and Maillard reactions take place. So proteins. Now we move into, we can move to proteins. We know the important sources of proteins, right? Meat, fish, egg, milk, things like that. And of course, there are grains that are rich in proteins as well. The most important class of biochemical molecules, well, they say it's the most important, but other things are also very important. The functions in living organisms are their major structural components, hair, nails, and those things, catalyze chemical reactions, that is, speed up chemical reactions. There are regulatory functions that proteins carry out, hereditary function in, like, there are called histone proteins. They are involved in arranging the chromosomes, and then transport function as an energy source when carbohydrates are not available. They can function as energy sources. There are 20 amino acids, and remember I told you about essential and non-essential amino acids. Now there are essential amino acids, and these cannot be synthesized by the organism. We cannot synthesize these amino acids, and there are 8 essential amino acids. These are given here. There are non-essential amino acids as well. Non-essential, we can synthesize these amino acids in the body, and the list is given here. General structure. Now let's learn about the general structure of proteins. Protein is made up of small units called amino acids. The small unit is called amino acid. Like in a chain, there are many beads. So one bead, the whole chain is the protein. One bead is an amino acid. So the chain is made of a lot of beads joined together, right? One bead, that's one unit, is an amino acid. Amino acids are made mainly up of carbon, hydrogen, oxygen, and nitrogen, and some amino acids contain sulfur. The amino acids, like one amino acid has a carboxylic group and an amino group. So let's look at the structure of an amino acid. This is the structure of an amino acid. There is this central carbon, right? There is this central carbon. A hydrogen atom is attached to carbon, R group, or a hydrocarbon. And the R group can be group hydrocarbon, hydrogen and carbon in group R, hydrogen. The other thing is common. Amino group, NH2 group, carboxylic acid group. Carboxylic acid can COOH में carboxylic acid penalty. So every amino acid has an amino group and a carboxylic acid group and an H and a hydrocarbon side chain, R group. You don't have to, like, this is just for clarity. A bond between two amino acids take place through the interaction, through the reaction between the carboxylic acid group of one amino acid and the amino group of the other amino acid. amino acid දෙකක් අතර bond එකක් හදනවා. ඒකට කියනවා peptide bond එක කියලා. මේක පෙන්නලා තියෙන්නේ මෙහෙම peptide bond එක. ඒක හදන්නේ එක amino acid එක carboxylic acid group එකයි අනික් amino acid එකේ amino group එකයි අතර වෙන reaction එකක් නිසා. Right? Don't worry too much about it. Just know that the bond between two amino acid is called a peptide bond. The structure of proteins is important as the shape of a protein allows it to perform its particular role or function. The shape of a protein is important as the structure is important because the structure gives the shape. The shape is important to carry out its function. හරි දැන් ඒකේ protein ලොකු chain එකක් ගත්තාම එක එක විදිහට ඒක නැමෙන්න පුළුවන්. එතකොට 3-dimensional structure එක එක protein වල වෙනස්. මේ shape එක ගොඩක් වැදගත් එයාගේ function එකට ගොඩක් වැදගත්. සමහර protein එකේ shape එක වෙනස් වුණොත් එයාට හරියට function එක කරගන්න බැරි වෙනවා. So when structure of proteins vary, then amino acid combination එක වෙනස් වෙනවා. So I told you that amino acid is one bead of a chain. නේද? The amino acid, we know that there are 20 amino acids. ඒකේ combination එක වෙනස් වෙන්න පුළුවන්. Sequence of amino acid within a chain ඒක වෙනස් වෙන්න පුළුවන්. ඒ කියන්නේ ඉස්සෙල්ලා තියෙන්නේ මොකද්ද? Alanine, glycine, valine, proline, threonine. අර ඒ තියෙන sequence එක වෙනස් වුණොත් මේ protein structure එක වෙනස් වෙනවා. වගේම spatial arrangement. Spatial arrangement of course ඉතින් ඒක වෙනස් වෙනවා. අපි ඒක කතා කරමු. يعني space එකේ ආ කොහොමද ඉන්නේ කියලා. coil එකක් විදිහට හැදෙනවද? peptide polypeptide එක කියන්නේ protein එක coil එකක් විදිහට හැදෙනවද? නැත්නම් pleated එකක් වගේ හැදෙනවද? pleated විදිහට හැදෙනවද? straight chains තියෙනවද? ඒ ඔක්කොම හේතු වෙනවා structure එක අන්තිමට හැදෙන්න. These differences are responsible for the differences in the taste, texture. Yes, taste, texture, because now these proteins are made of the same 20 amino acids, but their combination and the sequence are different, and because of that we get different forms. But chicken muscle like fish muscle, milk, curd, ඒ හැම එකේම appearance එක රස texture එක ඔක්කොම වෙනස්නේ. ඒ මේ protein වල තියෙන වෙනස්කම් හේතුවෙන්. When we talk about the structure of proteins, we are looking at 4 different levels: primary structure, secondary structure, tertiary structure, and quaternary structure. Then with the primary structure is the amino acid sequence. What we chain එකක් මොකද bead එකක් වගේ මේ හැම එකක්ම amino acid එකක්. හරිද? The sequence එක වෙනස් වුණාම එක වෙනස් වෙනවා. අපි primary structure එක කියලා identify කරන්නේ protein එක amino acid sequence. The secondary structure කියන්නේ local local structures. අපි ඔක්කොම දිහා බලන්නේ නැහැ. polypeptide chain එක සම්පූර්ණ එක දිහා බලන්නේ නැහැ protein එක. locally කියන්නේ එයා තනින් තන මොකද යාට වෙලා තියෙන්නේ කියලා බැලුවොත්. පොඩි segments බැලුවොත් සමහර ඒවා helices හදනවා. අපි alpha helices කියනවා. ගොඩක් තියෙන ඒවාට beta sheets කියලා જાතියක් හදනවා. random coils හදන්න පුළුවන්. ඒවට අපි කියනවා secondary structure කියලා. මේ පෙන්නලා තියෙන්නේ මෙතන. මේකට කියනවා alpha helix එකක් කියලා. This is a beta pleated sheet. This is a random coil. Tertiary structure කියන්නේ tertiary structure කියන්නේ three-dimensional structure එක. හරිද? 3D වලින් අපි බැලුවොත් as a whole the whole polypeptide chain අපි 3D එක කොහොමද ඉන්නේ කියලා බැලුවොත් that is called the tertiary structure, and that the tertiary structure is made due to the hydrogen bonds, strong ionic bonds, disulfide bridges, hydrophobic interactions. Then මේ වගල ඉගෙනගෙන තියෙනවා except disulfide bridges. මේවා නිසා තමයි මේ tertiary structure එක එකට ඒ විදිහට හැදිලා තියෙන්නේ. දැන් මේක අපි බැලුවොත් if we look at this protein, බලන්න මෙතන hydrogen bond එකක්, oxygen and hydrogen අතර hydrogen bond එකක්. ඒක hydrophobic interaction එකක්. හරිද? මේවා non-polar hydrophobic interaction එකක්. එතන ionic bond එකක්, ammonium ion එකකුයි carboxylate ion එකකුයි ionic interaction. මේක තමයි ඔයගොල්ලන් දන්නේ නැති එක disulfide, ඒ කියන්නේ sulfur අතර bond එකක් හදාගන්න පුළුවන්. Disulfide bridges. Quaternary structure is the fourth level. So if the three-dimensional structures join together to form a bigger structure, the bigger structure is called a quaternary structure. That is the fourth level. Then we are going to have a brief look at the denaturing of proteins. So we know that there is a shape of proteins. So without breaking the peptide bonds, that is without breaking the bond between amino acids, we can disturb the intermolecular forces. Intermolecular වෙන්නේ නැහැ. සමහරට එක molecule එකේ නමුත් අපි බලුවොත් hydrogen bonds, hydrophobic interactions, ionic interactions වගේම අපිට වෙනස් කරන්න පුළුවන්. අර peptide bond එක කඩන්න නැතුව, covalent bond එක කඩන්න නැතුව, right? So when that happens, we call the protein is denatured and the structure is lost. It can change the quaternary structure, tertiary structure, and secondary structure. So effects of denaturing. Altered solubility. Loss of functional properties. Functional තව මොකක් හරි molecule එකකට bind වෙන්න තියෙනවා නම් ඒක බැරි වෙනවා. එහෙම functional properties. ගොඩක් කියන්නේ වෙනස් වෙන්න පුළුවන්. Loss of biological activity. Improved digestibility, emulsifying and form properties. That of course can happen. Improved digestibility, emulsifying and form properties. Again, like ice cream එක උනත් ඒ texture එක පවත්ව ගන්න proteins ගොඩක් උදව් වෙනවා. Like if we take marshmallow, we beat gelatin, so we are incorporating air and changing the structure of the proteins through beating. It's a physical thing that we do, right? The protein gets denatured, air is trapped, and we get the marshmallows, right? And digestibility එක වෙනස් වෙනවා. මේවා examples of this is now this egg, not the yolk, egg white consists of proteins. Egg albumin කියලා එහෙම අහලා ඇතිනේ. Protein. Then first it's a liquid. When we fry it, it becomes solid and the color changes to white. So it's a irreversible denaturation of proteins. Irreversible. You can't get the original egg back. Occasionally reversible. අපි චුට්ටක් beat කරලා නතර වුණොත් it can go to the original form. Especially, say we take egg white and we beat a little bit, and if we stop, then it can go back to the original form. But if we do this continuously, the story is different. This can be done, denaturing can be done by chemical agents or by physical methods. Physical methods is to increase the temperature, mechanical treatment, hydrostatic pressure, irradiation, things like that. And then if we can use chemical agents such as acids, alkalis, heavy metals, urea, ethanol, and things like that. So functionality of food proteins. We talked about functional properties, didn't we? So these are the properties, the functional properties of functionality of proteins. The physical chemical properties that influence the behavior of protein in food system during processing, storage, preparation, and consumption. Right? So 3 categories. Due to protein-water interactions, we can change the viscosity, cohesion, and adhesion. Due to protein-protein interactions, we get gelation and dough formation. Make a dough formation. Dough kapita, we can make doughs using wheat flour. But if we try to make a dough using rice flour, do we get the same texture and same properties? Dough එක අදින්න එහෙම පුළුවන්ද? අපි හාල් පිටි දැම්මොත් instead of wheat flour. That's not possible, right? This dough formation is possible because of gluten, a protein in wheat flour. Right? Protein interaction, gelation, වෙන්නත් පුළුවන්. Surface properties, I told you about ice cream and marshmallow, emulsification, formation, and things like that. Now let us have a brief look at lipids. So these pictures are examples of foods that are rich in lipids, right? So if you look at the introduction, so lipids are a broad group of chemically diverse compounds. We can't say, like, we know that carbohydrates are made of sugar units, proteins are made of amino acids, but we can't say lipids are made of something because it's a group of different compounds, but they are solubles in organic solvents. They are not soluble in water. So lipids can be either fats or oils. Fats are those that remain as solids at ambient temperature, that is under room temperature. If a fat is a solid, if a lipid is a solid, we call it a fat. And at room temperature, if a lipid is a liquid, then we call it an oil. Lipids are mostly non-polar, such as triglycerol, cholesterol. Sometimes they are polar, such as phospholipids. Yes, සමහර ඒවා non-polar. ඒවා ගොඩක්ම oil වල වගේ තමයි දිය වෙන්නේ. Organic solvents වල. polar නැහැ. දැන් අපි දන්නවනේ මොකද්ද polar non-polar කියලා. එතකොට polar නැති ඒවා ගොඩක් තියෙනවා. ඒ වගේම polar. ඒ කියන්නේ partial negative charge එකක්, positive charge එකක්, එහෙම නැත්නම් negative positive charges තියෙන ඒවා. ඒ කියන්නේ polar ඒවා තියෙනවා. example එකක් තමයි phospholipids කියන්නේ. ඇත්තටම phospholipids තමයි අපි සෛලයක් ගත්තාම ඒකේ membrane එකේ තියෙන වටේ තියෙන membrane එකේ තියෙන phospholipids. සෛලයක් ගත්තාම ඒ වගේම බිත්තරයක egg yolk එකේ ගොඩක් තියෙන්නේ phospholipids. ඒව polar. Ionic නෙවෙයි, but they are polar, right? Polar කියලා දැන් හිතන්න polar lipids. They are polar lipids. They don't behave as ionic compounds, but they behave as polar compounds. That is what I wanted to say. So major lipid components are fatty acids, acyl glycerols, phospholipids, sphingolipids, sterols, waxes, and miscellaneous lipids. Now let's have a brief look at what these things are. Fatty acids, acyl glycerol, phospholipids, sphingolipids, sterols, waxes, and miscellaneous lipids. So these are major lipid components. We are going to briefly look at what these things are. So let's first look at fatty acids. Fatty acid. Acid because these molecules have a carboxylic group, acid. And fatty because the rest is a hydrocarbon chain. Hydrogen and oxygen, hydrogen and carbon, hydrocarbon. It has a carboxylic acid group, acid, fatty, because it has a hydrocarbon chain, right? Most fatty acids have an even number of carbons. Most fatty acids have an even number of carbons, mostly from 14 to 28. But we can actually find odd-numbered and branch chains from microorganisms and dairy fats. Now, let's look at what these acyl glycerols, right? So, let's look at a triacyl glycerol. Triacyl glycerol. So, glycerol molecule is shown here, right? The glycerol molecule has 3 OH groups. OH, 3 OH groups. හරිද? දැන් අපි fatty acids මෙතන ඉගෙන ගත්තානේ. Fatty acid එක කියන්නේ මොකක්ද කියලා. දැන් මෙතන glycerol වලට fatty acid 3ක් එක්ක interact කරන්න පුළුවන්. Right? One glycerol can interact with 3 fatty acids. ඒවා interact කරපුවාම හැදෙන එකට තමයි අපි කියන්නේ triglyceride කියලා. Triacyl glycerol කියලාත් කියනවා නැත්නම් triglyceride කියලාත් කියනවා. Triacyl glycerol කියලාත් කියනවා. Right? එතන 3ක් react කරපු නිසා tri. 2ක් react කරොත් diglycerol, diacyl. 1ක් react කරොත් monoacyl glycerol. දැන් අපි ඉගෙන ගත්තා fatty acid කියන්නේ මොකද්ද? මොකද්ද acyl glycerol කියලා කියන්නේ? මම briefly mention කරා මොකද්ද phospholipids කියන්නේ කියලා. Briefly mention කරා phospholipids කියන්නේ මොකද්ද කියලා. ඔයගලන්ට අනික් ඒවා නිකන් Google එකකින් චූටි the cholesterol කියන්නේ මොකද්ද කියලා නිතරම අහලා තියෙනවා. නිකන් structure එක බලන්න for just to get an idea. මේ waxes අපි අහලා තියෙනවා. Apples are coated with waxes so that we can keep apples for a longer period of time without letting the apples deteriorate. එහෙම මේ චුට්ටක් ඒවා පොඩ්ඩක් බලන්න. they come under they are considered lipids. එතකොට දැන් මෙතන this is quite interesting. දැන් cloud point කියලා අපි එකක් define කරනවා liquid oil වල. ඒ කියන්නේ cloud එකක්. අපි temperature එක ඉස්සෙල්ලා වැඩි කරනවා. Right? Temperature වැඩි කරපුවාම clear liquid එකක් එනවා. Then we gradually reduce the temperature. අපි අඩු කරගෙන එද්දි නිකන් cloudiness එකක් වගේ යන්තම් appear වෙන එකට කියනවා cloud point කියලා. ඒ කියන්නේ අපිට clear liquid එකක් විදිහට තියාගන්න ඕන නම් cloud point එකට වඩා වැඩි temperature එකක් අපි තියාගන්න ඕනේ. clear liquid එකක් ඕන නම්. අපි temperature එක අඩු කරපු ගමන් cloudiness එකක් එනවා. එතකොට අර specific temperature එකට අපි කියනවා cloud point කියලා. එතකොට smoke, flash and fire point. ඒවත් තියෙනවා. හරිද? දැන් smoke එකක් කියන්නේ So these are very important. Smoke, flash, and fire points are very essential in selecting oils to use at high temperature. Then baking and frying වලදී අපි baking and frying වලදී high temperatures වලට යනවා. අපේ oil එක අපි ඒකට suitable ද කියලා හොයාගන්න තමයි අපි මේ smoke, flash and fire points ගැන study කරන්නේ. Smoke point එකේ is a temperature at which the sample begins to smoke when tested under specified conditions. හරිද? දැන් අපි specific conditions temperature එක එහෙම බලලා මොන temperature එකේදී smoke කරන්න යන්නේ. Smoke එකක් අපිට දුමක් පේන්නේ මොන එකේද කියලා වගේ අපි දැනගන්න ඕනේ. දැන් olive oil වගේ ගත්තාම smoke point එක low. Ghee oil වගේ smoke point එක high. එතකොට අපිට smoke එක ඕන නැත්තම් smoke වෙන්න ඕන නැත්තම් ඒ temperature එකට වඩා අඩුවෙන් තියාගන්න. Flash point is a temperature at which we can see a flash, a fire. Fire appears at any point on the surface of the sample due to ignition of volatile gaseous products. Flash point. Flash point කියන්නේ මේකක් මේ නිකන් පොඩි flash එකක් එනවා and at any point on the surface of the sample. Then fire point ගත්තොත් it catches fire. It's dangerous to us, but some chefs, some people like, they know how to work with such oils to attract the viewers. They know how to use the fire point to attract the viewers, but it is very dangerous for us if it happens. So we should very carefully look at the smoke, flash, and fire points of oils before we do something. Before we use the oils at high temperatures. So, so in foods, triglycerols are the major type of lipids in foods, right? So we know that there are lipids, that's the big group. Triglycerides come under lipids. Triglycerides are the major types of lipids in food, triglycerols, right? Then lipids play important roles in food. They affect the texture. කොහොමද texture example එකක් කියන්න? Lipids. අපි chocolate ගත්තොත් cocoa butter වලින් හදන්නේ. cocoa butter දානවානේ and liquor. ඒ crystals, lipid crystals වලින් තමයි අපේට taste එක හම්බ වෙන්නේ. දැන් ඒකේ texture එක හොඳට තිබ්බොත්. ඒකම අපි chocolate එක fridge එකට දැම්මොත් do we have this, do we get the same texture? No, right? So එතන lipid එක ලොකු role එකක් කරනවා texture එක determine කරන්න. ඒ වගේම appearance, flavor. Lipids play important roles in food. So reactions of lipids, there are many reactions of lipids. Lipolysis. Lipolysis means අපි පොල් තෙල් අරන් තියෙනවා මං හිතන්නේ එකපාරක් හරි ඔයගොල්ලන් ජීවිතේ මුඩු වෙනවා කියන එක දැකලා ඇති. හයිඩ්‍රොලිසිස් එකක් වෙන්න පුළුවන් lipids වල. ඒ කියන්නේ water molecules නිසා lipid molecules කැඩෙන්න පුළුවන්. එතකොට rancid flavor, ඒ කියන්නේ මුඩු රහක්. ඒ වගේම හැබැයි ඒකම cheese එකේ අර mature වෙද්දි flavor එන්න ඒක හොඳ side එකක් lipolysis වල. ඒකත් මෙයා lipid oxidation. Oxidation එකත් rancidity වලට බලපානවා. Rancidity cause වෙන එකක් තමයි lipid oxidation කියන්නේ. Off flavors, toxicity වෙනවා lipid oxidation නිසා. hydrogenation to make margarine. කොහොමද margarine හදන්නේ? කියන්නේ sunflower oil වලින් මේක හදලා තියෙනවා කියලා. Oil chemically අපි ඒක solid කරනවා. Hydrogenation කියන්නේ hydrogen ඇතුළට දාලා මේ අපි chemically ඒක solid එකක් කරනවා. That's called hydrogenation. That is another reaction of lipids. Right. And I think so do you have questions?
Recording stopped.
Do you have questions? Right, I'm sure you.
Excuse me.
Yeah. Yes. I will upload the slides. Right. And like before you forget the things that you learned today, please try to answer the questions from the right?
Madam, do we want to remember the structures of these lipids and
No,
etc.
no.
for the exam?
No, you don't have to. You don't have to remember the structures.
Okay, madam.
And yes. Okay, then let's stop for now. For today, I hope you had a fruitful session. Study hard. Before you forget, do the we have to give you a quiz. We have to give you probably multiple choice questions. I'll talk with Dr. Gimhani. I think she will give you a quiz. Yes, she will upload the material. I'll talk with her. Some model questions are also there. Chapter 9. Yes, that is a problem. I forgot to tell you. Chapter 9, you have to read chapter 9. And for take home assignment, you have to answer the top three questions given at the end of chapter 9. There are 3 questions. Three review questions. What are agrochemicals? What are pesticide formulations? What are the advantages and disadvantages of using agrochemicals? So right answers, I think I will ask Dr. Gimhani to mention the maximum page limit, maybe 3 or something. So answer the 3 questions and submit on the day of the examination. Yes, there are 3 review questions of chapter 9. So answer the 3 questions and bring the answers on the day of the examination, because we consider the answers of the 3 questions as your home assignment. Right?
Excuse me, madam.
Yes.
Madam, Gimhani say last day that question is discuss advantages and disadvantages of using agrochemicals in plantation sector only. That question. So this 3 questions. So what?
She said the 3rd question is that advantages and disadvantages. But answer the first 2 questions as well. Very short answers. For the first two questions, what are agrochemicals? A very short answer has to be given. What is a pesticide formulation? Very short answer. What are advantages and disadvantages of using agrochemicals in the plantation sector? That's okay. Altogether, the page number, I will ask her to mention, give the information on LMS. I think 3 pages is more than enough. You don't have to write lengthy reports.
Double side though, madam? Single side?
Single side, 3 pages.
Okay, madam. Thank you.
Fine.
Ma'am, chapter 9 will come to the exams.
I don't know. You have to study all the chapters.
Okay.
I can't guarantee, but theoretically you can get questions from any of the chapters on the course module.
Excuse me, madam.
Yes?
What kind questions can we come in exam?
Actually, we are going to show you some model questions. We will upload that on LMS. Obviously, you will have multiple choice questions, structured essay questions, and essay questions, right? So we will upload some model questions.
Okay, madam. Thank you.
Right. The last chapter is about the practicals, right? So you will do the practicals on the practical day. I think next week.
Yes, madam.
Next week, right? So you will do. There's a titration, chromatography, paper chromatography, and UV visible spectrophotometer. These 3 practicals will be done next week. Okay. No, you don't have to memorize the structure of molecules. We won't ask you to know. Yes, you have to write the assignment separately and bind it properly and bring it at the day of on the day of the examination. Write your registration number, name, and write this is a home assignment of this course. Write the question and give the answers. Any more questions? You're welcome. Okay, then let's call it a day. Do the exam well and bring the take-home assignment.
Thank you, madam.
Thank you, madam.
Thank you,
Thank you,
madam.
madam.
Thank you, ma'am.
Thank you, madam.